You will go from knowing absolutely nothing about AI research to creating, coding, and training your own large language model and publishing a research paper or a technical report like this on the language model that you trained. Zero knowledge and experience required by you. I will cover everything in this course. You can watch this video on increased speed, for example 2x speed. And by the end you will have this large language model that you trained and created yourself. So if you prompt it, for example, the future of artificial intelligence, it will generate text that's coherent and good. So the future of artificial intelligence and machine learning is essential for anyone looking to understand and manage, etc. So you see how it speaks coherently with proper grammar and it has knowledge. Here are all of the lessons that we will be learning. It goes from math, PyTorch, neural networks, transformers. So again, you don't need to know anything right now and you will learn everything, publish your first AI research paper and get into the field. You will train your language model for free on Google Colab, or if you want to make it even better, I will show you how to rent GPUs from Hyperbolic. They gave me free compute so I can make these tutorials, so I would like to thank them. However, if you're just a beginner, I will show you how to do it for free, so don't worry, you can learn for free. The language model itself is quite good. Once upon a time in a distant galaxy lived an incredible little girl named Lucy. And I trained it for just 5 minutes on Hyperbolic's setup. If you train on Google Colab, then it will take some more time, but anyways, you will be able to create a very good model anyways. Even if there are some mistakes here, that's okay, I just trained it for 5 minutes. First of all, guys, I'm done with all of the AI companies and labs keeping all of their AI research secret. We are creating AI research lab and community where we open all of our research and create courses on how we did it so everybody can learn AI research and contribute to science. In his recent interview, researcher behind ChatGPT, Ilya Sutskever, said that we live in a world where AI research ideas are not discussed publicly, and we are about to end that. First thing I want to say is you don't need thousands or millions of dollars or compute. Large language models, or I should say transformers, were invented on equivalent of today's 1 or 2 GPUs. So just 1 or 2 GPUs They invented large language models using that. And in our Discord, there are some high schoolers who are inventing new optimizers on just laptop CPUs that don't even have GPUs. So free GPU by Google Colab is perfectly enough for you. And as you learn more, people will give you compute. This is what we will learn. This is the full curriculum. Starting from math functions, derivatives, vectors, gradients, matrices, probability. Then going to PyTorch, we have a bunch of Tensor Operations, classic PyTorch fundamental operations. Then neural networks, coding, creating single neuron from scratch. Then building a layer of neurons, activation functions, loss function, backpropagation, optimizers, and more. And finally, transformers and large language models. So tokenization, data loading, attention mechanism, rope, and mixture of experts. Guys, first step will be for you to click this link in the description that goes to github.com/vukrosic/blueberry LLM course. And then here, this is the code. So you can git clone this locally. Now, if you don't know what that is, don't worry. I will show you how to run this from this website itself using Google Colab. Just wait a moment. And if you know how to git clone, then I recommend here in course, you have all of the notebooks. You can just click math or whatever the notebook and then open it and run it locally. Now you can just open this course folder and in the math click this first Jupyter notebook, and there are a few ways you can run this. You can run this in your local environment. Just run it on your PC by clicking this execute button. Now it may ask you to select kernel, so in this case I will just say Python environment and I'm gonna choose any of them. This one will work. If it doesn't work, you can try different ones. But this one works because we have this green tick here. Another way to run it is to go to the GitHub repository. So just click the link below the video, this github.com/my name, blueberry, LLM course, etc. Copy this URL and go to Google Colab. And then File, Open Notebook. And then you can click GitHub and paste this URL here. I think I will remove this. Oh, actually, this works. Okay. And now I have a list of all of the notebooks here. Yeah, all of the notebooks are here. So I'm gonna click the first one, open it. Although this way you will have to open them one by one. So I actually recommend you just open it locally. But this also works. Here I would just click this start button, run anyway. There is no issues with this notebook. You can trust me, there is nothing here. And we will start our tutorial now. First, we have a linear function, y is equal to 2x. So if x is, let's say, number 2, then y will be 4 because y is 2x. And you can see here that if x is 2, y is 4. It goes here. And this is the linear function. I will not spend too much time here, but you can just check it yourself. A little bit read this. I will also click this button, Run All, to run all of the cells, so I don't need to run them one by one. And in the next one, we can see that depending on this coefficient next to x, it determines the slope of this linear function. So is it 1, 2, 3, 0.5, -1? So if it's -1, it will be kind of reversed like this. If it's positive, it's gonna be like this in these two quadrants. You can play around and check this. If you go up here, you can maybe change some of the k values here. And then this is how we plot and draw the function. So you don't need to understand that. Below we have a quadratic function, and so y is equal to x squared. I want you to just understand the shapes. So a quadratic function will actually grow quadratically. In the beginning, you see it doesn't grow so much, but the larger the x, y will be square of the x. So y will grow even faster the larger the x, because when you square big number, the square will be huge, even bigger number, a lot bigger. And this is the problem with attention mechanism and transformers. I will talk about that later. But in large language models, the more tokens you have, the more text context you type to ChatGPT, it needs to do quadratically more compute. For every new word or token, it needs to do like x squared more compute. This is how it's scaling. And we will talk about this later. One important thing to notice is that y is always positive, 0 or positive number, because when you multiply two negative numbers, so -2 times -2, it's gonna be +4, because minuses cancel out. But if we look at the cube, now cubes are no longer cancel out, because now you multiply negative number 3 times. So minus times minus gives negative number. So y will now be negative for negative x numbers. And cube will also grow faster than the square function. So those are the things you need to know. Now let's look at the square root. I just want you to remember like these characteristics of these functions that I'm telling you. So square root actually in the beginning, while x is small, it grows fast or faster. Then later, so the bigger the x, the slower the growth of y. It's kind of inverse of the square function. Square root is kind of slowing down the growth. And then we have exponential functions. So 2 to the x, 2 power x, or maybe 3 or whatever the number power x. So this grows fastest. And you see the slope here. This grows faster than the x power 2. So 2 power x grows faster than x power 2. And you see how for very small, or for, I should say, for negative x numbers, you get small y that's lower than 0, between 0 and 1. Remember, if you say 2 power minus 3, that's gonna be same as 1 over 2 power 3. That's the math rule. So 1 over 2 power 3. So it will always approach 0, but it will never be 0. And let me show you sine function. So this is a periodic function. You see how as we increase x, the y is kind of oscillating. So this is used so often. For example, this is used for the large language model to know positions of the words. Which word comes before which word. We will see more about this later. Now you can compare these functions. You see that x is always the same, 0 to 5. But look at quadratic, y is showing from 0 to 25. Exponential goes from 0 to 30. I told you that exponential is growing faster than the quadratic. But the square root, it's slowing down, actually. So it goes just from 0 to 2. Let's look at derivatives. This is important for how neural networks learn. And for, well, that's the most important, but many other things as well. So I will just go down to this image. You see we have our function. This is a linear function. And the derivative of that function will tell us the rate of change of that function. So growth or decline or whatever. But you see, a derivative here is always 2, which means at any point, if you move a little bit on x, it will move by 2 times that amount of y. And we can see that on the graph. It goes from 0 to 2 on x. On y, at that point, it will go from 0 to 4. Now, there is a catch. Derivatives are only showing at that specific point. So, if we look at derivative of 2 is 2, that means at this specific point of 2, it's growing by 2, by 2x. Just around that specific point a little bit. So if I move to 3, 4 on x, derivative might be different. So that's why I should not give example. If we move from 2 to 4, this will move by 2x, because by the time we move to 4, the derivative might change. In this case, we are lucky. In this case, its derivative is always the same. So I can give example. If we move this big distance, then the derivative, then the y will 2x. But you will see later that this is only case for the linear function. I'm gonna show that on different examples. So let's see the derivative of x squared. So here, the derivative will actually be 2x. So now, if I pick this point 1, at this point 1, the slope, the growth of y is 2.1, 2 times 1. So, which is 2, okay? But check this out. If I pick this point of 2, where x is 2, the derivative here is 2 times x, which is 2 times 2. So, derivative here is 4. So, it means that if I move on x a little bit, y will increase 4 times that what I moved. And here at x3, derivative or growth or rate of change, I should say, is 2 times 3, which is 6, which means if I move a little bit on x around 3, the y will move 6 times. That's why I told you it's not a good example to say if we move from 2 to 3 because derivatives are different there. So if we move, so if I want to explain the derivative, I will say if we are at 2, derivative is 4. So if I move just a little bit around 2, the y will increase by 4 times my movement. But I should not say if I move from 2 to 3, because by that time the derivative will completely change as well. It will not be 4, it will be 6 now. Okay, so you may rewatch this part if you didn't kind of get it. I also want to mention that it kind of makes sense. If I say what is the change, the rate of growth here, well, you can see here that y is actually 2 times x. So it makes sense that the derivative is 2, because y is 2 times x. The rate of change is 2 times x. And then if I say what is the derivative of x squared, now this is less intuitive. So here you would just use the rules you learn by heart of how to calculate derivatives. So for example, here you would put this exponent in front of the x, the variable, and say exponent minus 1. So that's the rule. You put exponent in front of the variable, so you get 2x, and subtract 1 from the exponent. So in the end you get 2 times x power 1, which is x power 1 is just x. So, okay, but I will not teach you more derivative rules. If you are interested, you may watch it on YouTube, but that's not necessary for now. So we will just continue. And let's take a look at this x squared again. So look at the derivative here. It's interesting. You have quadratic function, the derivative is linear function. You have linear function, derivative is constant. So derivative is 1 power less than the function. If you have squared, so the maximum, the biggest term is, biggest power is squared, derivative will be power 1. If the biggest term is 5, the biggest term in derivative will be 4. So you can see the rate of change at any point here. You see 0 at 0, the rate of change is 0, but at 1, rate of change is 2, at x is 2, rate of change is 4, at 3 it's 6, just like I manually calculated. So you can see that as in this quadratic function, as we increase x, the y is growing, starting to grow a lot faster and faster. Below we can visualize these tangent lines. This is like a slope. So here slope is 2, slope is 4, at this x is 2, etc. Slope is minus 2, minus 4. This is similar. This all kind of goes back on itself. Like this is like a linear function here. Now I have some common derivation rules. I'll quickly show you, but we may not actually need it. As I said, you have x to 4. You put 4 in front of the x, and then say this exponent minus 1. So you get 4x power 3. That's one rule. So what is the derivative of this x power 3 function, cubic function? Well, this is the derivative, so it's 3 times x squared. First, we can look at vector as an array of numbers. Here we have a vector that's 3, 4. It can be any array of numbers. And we can also look at these numbers as coordinates. So 3, 4. I say here 3 on x and 4 on y. So that's this dot here. And we put an arrow from center to 3, 4. You get a vector. Vector has length and direction. And this is so important, used everywhere. For token embeddings, for everything. Well, the whole large language model is processing vectors. It's used everywhere. Large language model sees the world in vectors and all neural network and matrices. And so this is used absolutely everywhere. We have this vector, which is, can you guess what the green vector is? So x is 0 and y is 5, so it's 0, 5. And it says here, I didn't even see it. And then we have minus 2x and 1 y. You can add two vectors by just adding corresponding elements at the same position. So first element here 3 plus first element here 1. The result will be 4. So the first element of the new vector will be 4, the x-axis. And then for y, we will just say 2 plus 3, which will result into 5. So it will be 4, 5, the resulting vector. So you can see v1 plus v2 is 4, 5. And interestingly, you can actually draw the first vector from the beginning. And then from that point, as if this was 0, 0, draw the second vector as if this was 0, 0. Or you can just move. They also say like move this second vector from the 0, 0 to the end of this vector. And this is the result. And so this big vector will be 4, 5. 4 on x and 5 on y. you can multiply vectors with scalars. So if you have vector 2, 1, 2 times this vector will multiply each of the coordinates. So 2 times 2, 1 will give 4, 2. Let's see examples here. 4, 2, or if you can half both of them, or you can multiply with -1 to change the sign. So multiplying vector, so if blue is our original vector, multiplying with 2, it will just make it 2 times longer in the same direction. So that's what multiplying with a scalar does. It stretches or squishes the vector, but doesn't rotate. Keep in mind, this is important. Rotating vectors and squishing and stretching vectors, that's very important in neural networks. Just remember that I mentioned it. There will be, we will talk about this later. So this is how you stretch or squish vectors. So this is squished by half, or reflected. This is reflected. We also want to be able to calculate length of the vector, or they say magnitude. This is similar to Pythagoras' theorem. So x squared plus y squared. And then when you sum them up, you get a number. You take the square root of that sum. But the difference is here you can have any number of elements, not just 2, not just x, y. You can have x, y, z, and any number. So you square them, all of that, you square them, and then add all of the squares, and then take the square root. It's just the second root, the square root. So it's not like if you have 3 elements, you take third root. No, you always take the square root. And that will give you the magnitude, the length of the vector. So let's see. 3, 4 vector has magnitude 5, and we can probably count it. If we were to count it, there should be, like, this blue one should be 5 long. It should be same length as this red one, because this is also 5 long. So blue and red should be same length, which they are. I recommend you play around with this more. You can understand it. And let's see dot product. So, of course, used everywhere as always. Here we will multiply x1 and x2. So first elements of the vectors plus multiplying second elements of the vectors. So in this case, 3 times 1 plus 4 times 2. At the end, this will give us a single number. The bigger the number, the more similar those vectors are. That's how we can calculate similarity. So you see that number here is 11 between the red and blue, and you see that red and blue are more similar than, let's say, blue and green, which are perpendicular, 90 degrees angle. So if you have 90 degrees angle, you will get dot product 0. That's how you know that they are 90 degrees angle. They are actually very different. And you see here, even more different if dot product is negative. So blue and yellow, dot product is negative, even more different. But usually we say that if they are perpendicular, they are very different. Subtraction works same as addition. You just subtract first elements and second elements by themselves. So 4 minus 1 and 3 minus 2. 4 minus 1 is 3, and this is 1 here. And it can work similarly to addition graphically as well. If blue is the first vector, red is the second vector, we can draw this vector that goes from tips and then move it back to 0 to see that it's 3, 1. That's graphical subtraction. But you need to draw from the second to the first and then move it to 0, 0. Let's go to gradients, go to the next notebook. Gradients are similar to derivatives. So if you have x squared plus y squared, the gradient, so first look at this gradient, 2x comma 2y. It looks similar to the derivative because derivative of x squared is 2x, or derivative of 2y is of y squared is 2y. But this is the difference. So first of all, in gradients, we will have multiple variables, not just x in the expression, but multiple variables. And For each of the variables, we will process them one by one. And this is what we will do. First, we take this variable and we imagine all of the other variables are constants, constant numbers. They are not variables. So when we process x, we imagine only x is a variable and we treat other variables as constants, and then we apply rules. So plus constant will actually, derivative of plus constant will be plus 0. So derivative of this whole expression is 2x plus 0, which is just 2x. And that's partial derivative of this function with respect to x. That's how you can say partial derivative of this function with respect to x is 2x, okay? Partial derivative of this function with respect to y, it's gonna be 2y, because now we are imagining that x is a constant. And when you have constant alone without it being multiplying the variable, which is in that case y, then that constant becomes 0. So this is the partial derivative. And so if we put them like that, it will be our gradient. Now you see that in gradient, for example, this one we have 2x and 2y. And this x and y are coordinates of the coordinate system. And so if we put some numbers instead of x and y, it will, whatever the vector we get, we will get some vector. So for example, if we put 1 for x and 1 for y, we will get vector 2, 2, because it's 2x and 2y. So vector 2, 2 will be like an arrow, vector 2, 2. And it will show us in which direction is the steepest ascent. So you see here, you see this 3D surface. You can take any, so imagine there is a plane, and then on top of this plane there is this 3D surface. So if you take any coordinates on this plane and you see where those coordinates are on this 3D surface, the gradient there, when you put these coordinates into the 2x, 2y, the gradient will show to the steepest ascent, steepest increase of the function. If this doesn't feel so intuitive, then you don't worry, like it maybe takes a few times to understand it. Now imagine we are looking at this shape from above. So this is what that shape would look like from above. And in the center, it's very flat. But because the formula for this shape is x squared plus y squared, and we remember that square functions grow fast as we increase x and y, the square functions will grow very fast. Here we have third, maybe z coordinate, or but anyways, around 0 it will be very flat. But as we move away, it will start to grow faster and faster. And you see that around 0 the arrows are very small, showing small gradients, small rate of change. And later arrows become longer, which illustrates that as we move away from 0, 0, the rate of change, the slope, is faster and faster. And also, these arrows are vectors that point towards the steepest ascent. So they point where it's growing, towards where. And in this case, they're always pointing away from 0 because it's just like very nice shape, nice function. But if you have like some random surface, maybe it can ascend this way and then descend and then go this way. Like it can be like. But anyways, those are two things you need to understand about gradients. So they are vectors that point to the direction of steepest ascent. And the bigger the vector, the steeper ascent. If at any point you are struggling to understand what I'm saying, it doesn't matter. You don't need to get stuck or overwhelmed or bored of one thing. You will understand it eventually. And you will be able to follow even if you don't understand everything. Just remember that in neural networks, we need to know where the steepest ascent is because we want to do something in the opposite direction. We want to subtract the vector. We want to move on this surface in the opposite direction of the steepest ascent. We want to move down, so the steepest down. Just remember this concept. We know where the up, we want to move down in neural networks, and we will talk about this later. This is because this will be the loss, the error function. So we want to minimize the loss, the error. So by finding in which direction to move down to make the error smaller, but I know this may sound very overwhelming or confusing, so I'm just mentioning for you to hear about this, and later you will understand it better and better. Now look at this function, 2x plus 3y. This is just a plane. This is like a sheet of paper. And if it's curved like this, it will always be ascending this way, up. If you go this way, you go up. And so these arrows are always going to be always in the same direction because it's just a plane. I should have showed you this picture. So this is what I was talking about. You see, in the middle at the bottom it's very flat, but as you go around it starts to grow faster and faster because it's quadratic function. And in neural network, this picture may not show the full arrow, but as I said, this is the ascent, and in neural network we will actually find the opposite or subtract. So negative gradient is the steepest descent. Let's go to matrices. So matrix is like it has rows and columns, but if this had just one row and multiple columns, that would be vector. Or if it just had one column and multiple rows, that would still be a vector. So usually when we say matrix, we think of something that has at least two rows and columns. So it's like a array of arrays. So you can say this row is first array, second array, third array, and there is array of arrays. So I don't want to confuse you. I will show you how we define matrix in Python. So it's first row, second row, and you see it's array of arrays. This array contains these two arrays. It doesn't have to be square matrix. It can be like more columns or more rows. Then if you have some matrix, you want to access the first element, you need to access by saying which row and which column you want to access. And the first will be the row, the second will be the column. So remember, in Python we start from 0. So the first thing has index 0. So 0 means, okay, so this is 0, row 1, row 2. So we want row 0 and this is column 0. So row 0, column 0, they intersect at this number 1. So that's how we pick number 1. That's how you pick number 1. This means I want row 0 and all of the elements in the row 0. So it will pick like this. It will pick 1 and 2, this vector. It will make it a vector. Okay, and this below means I want all of the rows from column 0. So all of the rows from column 0. So that's the column 0, the first column, and all of the rows. So 1, 3, 5, all of the numbers. You see, it gave us this array 1, 3, 5. Adding two matrices is very easy. 1 plus 2 is 3. 2 plus 5 is 7. You just add elements on the same index. You can also multiply matrices with scalars. It works same as vectors. So 2 times matrix A will just multiply each element with 2. So it will be 2, 4, 6, 8 now. Matrix multiplication is a bit more tough, so you need to understand this too. So it will take some practice for you. You are going to do dot product between row and a column. So what does that mean? Look at this formula here. Okay, so we have first row and first column, and so this length of this row and length of this column must be same. So it's 3 and 3. Okay, if this was 4, we cannot multiply it. And this is the formula here. So you do 3 times 0. So first elements, 3 times 0, plus multiplying second elements, 1 times 2, plus multiplying third elements, 0 times 0. At the end, the answer is 2. And we write the answer here. at the intersection, and the intersection here is first row, first column, so you write it here, first row, first column. And then you do first row, second column, you write it here. You can see that this inner dimension must be same. So I didn't explain. So if you have a matrix, first you write number of rows. So 2 rows, so that's 2. And then 3 columns, 1, 2, 3. And here we have 3 rows, okay, and 2 columns. So this number of columns and this number of rows must be same. And we cannot swap. If we swap, well, in this case we can, because then it will be 2 and 2 will be the same. But you need to be careful, and if you swap, you will get completely different result. So what I'm trying to say is swapping order of matrices is not going to yield same result. It's a different thing. And you need to make sure that these inner dimensions are same, equal. And they will cancel out, so at the end you will just get the outer dimensions, whatever they are, for the resulting matrix. So that's how matrix multiplication works. You will not do this manually, but this is one of the fundamental things that will come up. You need to know this. But even if you don't understand it right now, you need to understand it eventually. So, as I said, don't get stuck too much on something, overwhelmed. Just try to follow and make it interesting. Transposing the matrix will swap rows and columns. So if you have 1, 2, 3, 4, 5, 6, now this column 1, 4 will become a row actually. This column 2, 5 will become row 2, 5, okay? And at the same time, this row 1, 2, 3 will become a column 1, 2, 3. Identity matrix. So if you say np or numpy.I and pass in the number, you get identity matrix that has zeros everywhere and ones on the diagonal. And when you multiply any matrix with this identity matrix, that matrix remains the same. So this will not change the matrix. This is like multiplying with 1. These are some properties. So most of the matrix operations are same as the normal numbers. It's just the matrix multiplication A times B is not same as B times A. So that's not same in general. Maybe there are some specific cases where it's same, but in general it's not same. And finally, let's look at probability. So you would define probability from 0 to 1. That represents from 0% to 100%. So probability 0 means impossible to happen. Probability 1 means certain to happen, will happen every time. And 0.5 means 50% chance. And so usually probability is denoted from numbers from 0 to 1. For example, 0.5. So if you have a fair coin, what is the probability to get heads? Well, it's the how many possible outcomes to get heads. It's just one. So you have one outcome for heads, one outcome for tails. So there is one outcome for heads, and total outcome is 2. 2 possible outcomes, heads and tails. So 1 over 2. Same goes for dice. You have 6 sides, and so outcome that the number is 6. There is just 1 out of those 6, and so total is 6. So the outcome is 1 over 6. But this division 1 over 6, 1 over 2 only works if each outcome has equal probability to happen. So then it's 1 over 6. But if one of the outcomes had a lot larger or different probability, I should say, then you cannot just divide like this. So before I talk about that, let's see this AND and OR. So what is the probability to roll 1 and 6 if we are rolling 2 dices? So we will multiply those two probabilities. So it will be 1 over 36. And what is the probability that we get 1 or 6? At first, it seems like it's probability of getting 1 plus probability of getting 6 because any of those would satisfy. But there is a catch. So if one dice is 1, there are all of these possible combinations. So the other dice can be 1, 2, 3, 4, 5, 6. And if one dice is 6, there is also 6 possible combinations where the other dice can be 1, 2, 3, 4, 5, 6. But you see, we are counting this one 2 times. So we want to subtract one of them because when we just add probabilities like this, we are counting the probability of 1 and 6 2 times. But we should just count it once. So that's why we subtract probability of 1 and 6, one of them. This is the probability distribution. So let's say you roll 2 dices and you sum up the numbers. What is the probability that the sum will be 2, 3, 4, etc.? Well, there is most ways to get number 7. So you can get number 7 if you get 2 and 5, 3 and 4, 1 and 6, yeah. So there is most ways to get number 7, and there is least ways to get number 2 or number 12, because you only get 12 if you get 2 times 6. And so in our simulation, if we just throw these dices a bunch of times, you'll see that the experimental outcome approaches the theoretical probabilities. And the more we throw, the closer it will be. So that's the law of large numbers. The more attempts, the more outcomes, the more samples, the closer the average will be to the theoretical probability. Expected value. So if dice can have 1, 2, 3, 4, 5, 6 values, and each of them has 1 over 6 probability to happen, then you would multiply each of the values with its probability. So in this case, it's gonna be a sum of all faces over 6, which will be 3.5. So you need to multiply each of the value with its probability. And in this case, because every probability is same, you can just sum all of the values and divide by 6. But you wouldn't be able to do that if probabilities were not same. Conditional probability. So what is the probability that we roll 6 if we know that we rolled an even number? Okay, so thinking about this, if we know that it's an even number, we know that we rolled either 2, 4, or 6. So what is the probability then that we roll 6? Intuitively, it's simple. It's 1 over 3 because we have these 3 possible and they have all equal chance of happening. But the formula would go like this. You would say probability of it being 6 and even. And thinking about it, if it's 6, it's also even. So then we just need probability of it being 6, which is this probability. And it's automatically even. So that's the probability of it being 6 and even, and divided by the probability it's even. So that's the probability. That's the law of large numbers. So as we sample more, for example, coin flips, we know that the average is 50% or 0.5. That's the probability. So as we sample more, it will approach this average, this theoretical probability. Maybe in the beginning it will get randomly, like you get a bunch of heads in the beginning, but with more samples it's approaching average theoretical. And that's it for the math course. And now we're gonna go on to PyTorch course. Starting with creating tensors in PyTorch, I'm gonna run all again. Import torch and import numpy as np. So this is a tensor, it's an array. So you can say torch.tensor and pass in this array. And you can check its shape and size. So, and shape and size are the same thing. So this has 5 elements. So the shape is 5. And if I scroll down, you'll see shape is 5, size is 5. You see it's the exact same class. You can create a matrix or a 2D tensor like this, just passing matrix, or a 3D tensor like this, so any amount of dimensions. And we can see that this has 2 elements, so the outer ones have 1, 2, and then each of them has 1, 2, and then each of them has 1, 2, so it's 2, 2, 2. You see the shape here, it's 2, 2, 2, and number of dimensions is 3, these 3 dimensions. You can create torch.zeros passing 5 to make a tensor of all zeros, and it's gonna be like this. Or if you pass 3, 4 as dimensions, you get all zeros like this. You can also create ones. Let me show you here. Torch.ones 5, torch.ones 2, 3 dimensions, which will create 2, 3 like this. And you can say torch.full 2, 3 dimensions with value 5. So this will fill this matrix 2 by 3 with all 5s. You see here. If you have NumPy array, you can convert it to PyTorch tensor by just saying torch.from NumPy and pass in the NumPy array. And you can convert tensor to NumPy by calling .numpy like this, creating tensors with random values. So torch.rand 3, 4, this will give you values between 0 and 1. I believe it's not including 1. You can also say a rand int between 0 and 10, so you will get values between 0 and 10 in this shape, and this will not include 10. Oh no, sorry, it's this one, not gonna include 10, so 0 to 9. And then you can also sample from normal distribution. So the values will be usually closer to 0. Maybe some will be around 1, but the further away from 0 you go, the less likely those numbers are to appear, although it can be any number possible, but it's the likeliness of being any number drops significantly the further away from 0 you go. So most of the numbers will be centered around 0. You can also scale, so you create random, and this will create between 0 and 1, and you multiply everything to 10, so you scale, so it will be between 0 and 10, without including 10 as a possible number. And you see these are floats and these are integers, so we used rand int here, and this is just random times 10. You can check data type of the tensor by saying .datatype. Usually you will use float 32, float 16, bf16, fp8, fp4. So you will not use 64-bit, those are too big. You will use 34 or lower, 32 or lower. And you will not use 64 integer in neural networks. So if you put 1.0, it will be float. And if you put 1, 2, 3, it will be integer. And you can manually set data type to float 32. So let's see below. We got float, integer 64, float 32. We can also convert by saying tconvert.float. We will convert from integer 64 to float 32, I believe. Yeah. So float 32 or just float, that's the same thing. 32-bit floating point number. Float 64 or double, that's 64-bit. Int is same as int 32 and long is same as int 64. here is the summary. This is what we went over right now. Now open the next notebook, matrix multiplication. And we know how to multiply them manually from the math course. So here you have this matrix and this matrix. You can just put this at sign and this will do the matrix multiplication. And let's check. So this matrix multiply this matrix gives this matrix. It's difficult for you to know intuitively what you will get because you need to do dot product between each row and column. So you're not going to know intuitively the resulting matrix. And so size 2, 2, 2, 2. And the size of the final matrix is 2, 2. You can also use torch.mathmul A and B. You will also get matrix multiplication here. Matrix vector multiplication works in the same way. We have 2 by 2 and this is just 2. Let's see here, 2 by 2 and then just 2. Now let's see what happens. If I say matrix multiply vector, it should automatically broadcast this from just 2 to 2 by 1. Because I told you, if you are multiplying 2 by 2 times something, then this dimension and this first dimension must be same. So then it can add like here 2 by 1. So it can just add one more. We'll see later this broadcasting. So anyways, the result is gonna be 2 by 1 as well. Or just 2 if you return it back. But let's not get confused by this. We'll see this broadcasting later and the dimensions and stuff. So batch matrix multiplication, we have this matrix 2 by 4 and then we have 3 of them. So we have matrix 4 by 3 and 3 of them. So here again we are multiplying this shape and this shape. So this and this must be same number. And then this will remain the same. We ignore these number of batches. And this is going to require some practice from you. So here it's going to multiply this matrix and this matrix. And you see 4 elements in a row and here 4 elements in a column. And it will multiply second and second, third and third. We have this torch.batch matrix multiplication, which we can use. And it's going to do the same thing as this matrix multiply, but here we are just multiplying the first matrices here. So the first matrix of this batch and first matrix of this batch. And it should be same or equal, I should say, to this batch matrix multiplication, the first matrix of it. Which it is equal. Are they equal? True. Next lesson, transposing tensors. I already talked about this in transposing matrices. So if you have this matrix, you transpose it, then now rows become columns. This column is now the row. So if this element 2 was at index 0, 1, after transposing it, it will be at index 1, 0. So swapping these size, shape, indices. You can also transpose specific dimensions. So if you have a 3D tensor, you can swap dimension 0 and dimension 2, which are first and third dimension. You see here, this is the innermost dimension 1, 2, and the outermost dimension would be 1 and 5. And now you swap them. So 1 and 5, but you're gonna need to get some intuition here. And 1 and 2 now became like outer. 1 and 2. So this is the first element of the outermost element. First element of the second outermost element. And these are elements of the innermost element. But you're gonna need to get some intuition to understand this. It will be simple once you understand it. You can just play around with this notebook and try different things. We can also use this permute, so our tensor.permute, and say second dimension, first 0th dimension. Let's see. Just like before, you see we have 1 and 5, which is now innermost dimension, 1 and 5. But those were first elements of the outermost dimension. Interestingly enough, 1 and 3 at exact same places as here, 1 and 3. You see 1 and 3 same places as 1 and 3. That's because we went from shape, the shape was like, we went from 0, 1, 2 to 2, 1, 0. So this one stayed at the same place. So we didn't actually move the elements of this dimension. It stayed the same, this second dimension. That's it. I just want to mention that if you transpose matrix 2 times, it returns to the same matrix. And if you do matrix multiplication and transpose the result, it's going to be equal as if you transposed the second matrix, but the order is very important. So the second matrix transposed, matrix multiply the first matrix transposed. If you swap them, it will not be same result. So this is the rule. Now we can go to flattening, reshaping, view, squeeze, unsqueeze. Flattening is converting tensor into array or to 1D tensor. So I'll show you example. Here we have this matrix 1, 2, 3, 4, 5, 6. If we flatten this matrix, we will make it just one array, 1, 2, 3, 4, 5, 6. Here you can see that if we call t, which is the name of this tensor, dot flatten, that's how we flatten this tensor. And we can specify the dimension where we are flattening. So if we specify the dimension is 0, it means it will first take this. It will just go element by element in the dimension 0. So this is the first element of the dimension 0. It will just write it. And then second element of dimension 0, it will write it. But let's see on a different example where we have this 3D tensor and we specify the dimension to be 1. So dimension index 1. Let's see, that's the second dimension. Let's see. So it's starting from dimension 1. So dimension 0 will remain. You see, dimension 0 is this outer brackets. And this outer brackets has one element, two elements. And because we are skipping dimension 0, we are starting from dimension 1, in the end we will still have one element, two element. But within this dimension it will be flattened. So starting from dimension 1 it will be flattened inside into a vector. Let's see reshaping. So what is the dimension of this matrix? Can you tell me? Okay, so it has 2 rows and 8 columns. So it's 2 by 8. You start from the outermost brackets. So this outermost brackets has 2 elements. And then inner brackets have 4 elements. So 2 times 4. But we can reshape it by calling t, which is the name of the tensor, dot reshape, and 4, 2. And now it goes from 2, 4 to 4, 2. Let's see what that does. So instead of being 1, 2, 3, 4 in the first element, now the first element will just be 1, 2. And then 3, 4, 5, 6, 7, 8. So it has now 4 rows or 4 elements in the outermost brackets and 2 elements in the innermost brackets, or I should say 2 columns also. You can also reshape it to just 8 elements. So now it will just be like a 1D tensor. All of these 8 elements will be in one array. So the dimension will just be 1D. You can also say -1. So it means figure it out. Figure out how many elements needs to be here instead of this -1. Which is going to be 8 because we already know there is 8 elements. And as I said, reshaping to 8 will just put all 8 elements because there is 8 elements in total, so it will just be one array. And -1 will do the same. It will figure out that if it is just like 8. Now if I told it to reshape to -1, 2, then it knows, okay, I have 2 here, so this -1 is gonna be 4, because there is 8 elements in total. Check this out. First of all, torch.arrange 24 will create numbers from 0 to 23. 24 is not included here. And then, so that's gonna be just one array. But I wanna reshape that array into dimensions 2, 3, 4. And remember, when you multiply these dimensions, the result must be the number of elements, which is 24 is the number of elements. So 2, 3, 4, let's see what we got. The innermost dimension is 4, which is this 4 elements, and then 3 is this. So 1, 2, 3 in these brackets, and there is 2 of these brackets. So that's the outermost dimension, 2. And I can then reshape it to 6, 4. So it's gonna keep this 4 as the inner dimension, and it will just now have 6 rows in the outer dimension. So a bit of intuition and playing around is necessary here, so you can understand what's happening and why it's happening. So view is similar to reshape, but view will not create a copy of a tensor, and reshape may or may not create a copy of a tensor. So what does that mean? If I have a tensor and it's 2, 4, and I view it as 4, 2 instead of reshaping it, now if I change any value in this tensor, it will also change the value in this other tensor from which it's viewed, because it's the same tensor in the memory. So view is just reshaping, showing difference. So you see that the first element is 1 in both of them. But then I set the first element to 99 in this view, in the second tensor, view tensor. But then both of them will have the first element at 99 because it's the same tensor. View doesn't create a new tensor. Reshape might create if it's not contiguous in the memory. So if the elements are not next to each other in memory, then reshape will still actually check if it still can create a view. If it can create a view, it will just create a view. It will not create a new tensor. But if it cannot create a view, then it will create a new tensor. Now let's see squeeze. So you see we have this array 1, 2, 3, and that's inside another array, and that's inside another array. So what is the shape of this? Well, we start from the outer array. It has 1 element, and then this has 1 element, and then this has 3 elements. So it's 1, 1, 3. And you see here the shape is 1, 1, 3, just as I said. But if I say that tensor.squeeze, it will remove. So squeeze will remove all of the dimensions of that are just 1. So let's see how we understand that. So you see we have 1, 1, 3. After squeeze it will just be 3. So now we will just have one array of 3 elements, and these outer arrays or arrays that have just 1 element will be removed. So let's see some other example. If we have this tensor that has 1, and then inside it has 3, and then 1. So this is 1, 3, 1. Because outer has 1, inner has 3 elements, and then each of the inner dimension has 1. So it's 1, 3, 1. And we will just squeeze dimension 0, so outermost dimension. And let's see the result. So first of all, shape is 1, 3, 1 originally. If we squeeze dimension 0, that means we are just removing the outermost brackets. And these inner brackets that just have 1 element, they remain, because we specify that we are just removing dimension 0. We can also squeeze just dimension 2. So now the outer brackets will remain, and this that has 3 elements will remain, but this dimension that encapsulates every element will be squeezed, removed. So that's the dimension 2. Remember, dimension 0 is the outer, dimension 1. Dimension 0, dimension 1, dimension 2. So dimension 2 is the last one here, the innermost dimension. Unsqueeze. This will add dimension of size 1. So this is reverse, the opposite of squeeze. If we have this tensor, just 1D tensor 1, 2, 3, 4, the shape will be 4. And if we say unsqueeze at dimension 0, then it will become 1, 4. So it means, what does that mean? It means there will be another brackets around this. Let's see an example I can explain easier. The beginning tensor has shape 4, and then we unsqueeze at dimension 0, so we add dimension around the outer dimension. So now it's 1, 4. So it means like the outer brackets have 1 element and the inner brackets have 4 elements. We can also unsqueeze at dimension 1. So that will now make this from 4 to 4, 1, which means every element here will get its own dimension. So it will be in brackets, just like it's shown here. So because originally this just has 1 dimension, so that's dimension 0. And if we unsqueeze at dimension 1, means we are just adding now 1 more dimension. So it's gonna be 4, 1. And 4, 1 looks like this. And maybe this will require some playing around for you to get the intuition. In the beginning it looks complicated, but later it's very simple to understand when you practice a bit. Let's see something interesting. If I say unsqueeze -1, this will add dimension at the end. So if the shape is 4, the dimension will be 4, 1. If the shape is 3, 5, once we unsqueeze at -1 at the end, it will be 3, 5, 1. You see, it will just add dimension 1 at the end. So here, it will just encircle every element with a bracket. So that's what's unsqueeze at dimension 1 is gonna do. So it will encircle every element with its brackets. So that's adding the dimension 1 at the end. The most common one would be unsqueezing at dimension 0 in neural networks because you wanna be adding batch size sometimes. And we'll see later what batch size is. Sometimes you wanna multiply some matrix and some matrix, but this matrix has maybe 3 dimensions, and this one has 2 dimensions. So you would maybe add another dimension to this one. So now on the out, so that's like a batch dimension. So then you can multiply 2 by 2 matrices, but there is a batch dimension outside as well. You need to make it same dimension. Okay, this is a bit complicated, but anyways, we would use unsqueeze to match the number of dimensions, and once we multiply it, if we need, we would use squeeze after to reduce unnecessary dimensions, if we have sometimes. Let's go to next notebook, indexing and slicing. When I tell you I want this element 5, how do you know quickly how to index it, how to take it out? So that's gonna be row 1 and column 1. So that's just gonna be T11. So here you would write T and the indices are 1, 1 to access that element. So this will require some practice from your side, maybe to be able to do it quickly. So T of 0 will give you the first row, okay? But if you want first column, or if you want to index a column, then you need to use this syntax. So you put this sign, column, which means all of the rows from beginning to the end. And then just 0th column, which is the first column with index 0. So this will give you column with index 0. So let me show you. This is our matrix, 1, 2, 3, 4, 5, 6, etc. And this will give us just the first column, which is 1, 4, 7. You see here, the first column, 1, 4, 7. T of 0 will give you the first row, 1, 2, 3. So this just requires some practice. slicing, now you want to get a range of things. So you want to get first two rows. So you can do it like this. You say T0 column 2, which means start from the 0th row and go until row number 2, but don't get row number 2. This is excluded. So this first index is included, this index is excluded. So it starts from 0 and 1 rows and doesn't get 2 row. It's just how it works. So let me just show you example here. Yeah, this will get you first 2 rows. And then in this case, where you say from 1 to the end, this will get you row with index 1 and until the end. So these 2 rows. And you can also say from beginning to 2. So this if you have number here, then it will be excluded. So it will just get you first 2 rows from beginning until index 2, but 2 is excluded. Okay, here it's included. If it's here, it's excluded. Okay, this requires some practice again. Slicing columns. Okay, so this is how you do it. You say, I want all of the rows, and then column with index 0 until column with index 2, but 2 is excluded. So this will give you 0 and 1 column. Okay, it will not give you 2 column. It will give you 0 and 1 column. So 1, 2, 5, 6. 1, 2, 3, sorry, here. 1, 2, 5, 6, 9, 10. And then here we will get all of the rows, but columns are from 2, including 2 until the end. So from 2 until the end, it's gonna be like these, and all of the rows. And lastly, you can say I want rows from 0 until 2, excluding 2, and columns from 1 to 3, excluding 3. So let's see. Rows are 0 and 1, because 2 is excluded, and columns are 1 to 3, which is just gonna be 1 and 2 columns. So it's gonna be 2, 3, 6, 7. If we go here, 2, 3, 6, 7. You can also create a Boolean mask. So this, you have t, and if you say mask is equal to t over 5, so t is our tensor, and you see this will create true at all of the values that are greater than 5, and false at all of the values that are less than 5 or less or equal to 5. So that's gonna be our mask. It will be same shape as, let's see, the mask. You see, it's gonna be also a tensor and has false where it's less than or equal to 5 and true where it's more than 5. And then you can say t and then put mask as index, and it will give you this tensor of all of the values that are true if you index it with this Boolean mask. You can also index conditionally. So you index t where t is greater than 5. And that will give you this tensor of these values, or where t is a even number. It will give you these values. You can also modify values with indexing. So if you have this tensor and you say t of 0, 0 equals 99. Now this will set this 0, 0 element at 99. So you see, after we use it now, this tensor is 99. You can also set entire row, and now it's gonna be this row. You can also set a slice, just as I told you. So if we set a slice, then it will be like this. And we can set everywhere where t is greater than 50, we can set to 0. And it's gonna look at this tensor because this is the original tensor. We have changed it. Now it has these values. So now when we call this function or task or line of code, then it will just change all of these to 0 because they're greater than 50. So that's it. I will scroll through key takeaways, but that's all you need to know here, and I recommend some playing around if you are curious about it, but don't get overwhelmed or bored. Don't like try to master it in like one day, or because it will take some time. So you can play around if you are curious, or you can just go to next lesson if it's boring. You will be able to follow my lessons even if you don't master everything immediately. And I will repeat this in future lessons as well. So you will understand it eventually. So we can concatenate or merge tensors. So using this torch.cat. And so we have this tensor and this tensor. And if so their shapes are 2, 2, 2, 2. And if I say torch cat and T1, T2 along dimension 0, and later we will see along dimension 1 as well what happens. So along dimension 0, we just kind of merge these outer brackets. So all of the elements in these outer brackets we've just put like next to each other. So we first put the elements, these are two elements, which is 1, 2, 3, 4. So we put 1, 2, 3, 4, and then we just continue with the second tensor, 5, 6, 7, 8, 5, 6, 7, 8. So because we are concatenating along dimension 0, we are just concatenating elements in the dimension 0 next to each other here. So let's see next example, maybe it will be easier to understand. So along dimension 1, now we are concatenating like this, the inner elements putting next to each other. So now it's gonna be 1, 2, 5, 6, like this, 1, 2, 5, 6, and then 3, 4, 7, 8. So now we kind of just merge these inner elements. So again, maybe some practice for you to understand this. So we can also concatenate 3 tensors. It's also gonna be 2 by 2 tensor and along dimension 0. So what's gonna happen here? We will just continue stacking these elements elements of dimension 0. And maybe I shouldn't say stacking because we actually have a separate stack command. So we will just keep concatenating these elements along dimension 0. Torch.stack creates a new dimension and stacks tensors. All tensors must have same shape. So again, we have this 2 by 2 and 2 by 2. And if I say torch stack and those two tensors along dimension 0, now instead of concatenating all of the elements, it will just create, like now it will concatenate these two entire matrices. It will create a new dimension outside, so dimension 0, and now it will just concatenate or stack these two matrices. It's a bit different. Notice that previously they were 2 by 2 matrices, and the new matrix is now 2 by 2 by 2, because we just concatenated stacked two of them. You can also stack among dimension 1 or dimension 2, and in this case all of them will be 2 by 2 by 2, so all of them will look same. So maybe this is not the best example, but let's continue. And to compare cat and stack, so cat will actually create, when you cat 2 by 2, 2 by 2, you get 4 by 2. And when you stack them, you get 2 by 2 by 2. And so you would, for example, use stack when you have multiple feature vectors, maybe multiple tokens, and you want to put them all into the same tensor. So you can use stack, it will create a dimension around and put them all into like a tensor. I have more examples here if you want to check, but that's all you need to know. And the last lesson in the PyTorch module, random arrange linspace. Actually, we had some of these. I is just identity matrix. We had this. So it will create this where it's 0 everywhere except main diagonal 1. Let me show you linspace. So we will create a vector or tensor that goes from 0 to 1, and then it has 5 values, and the space between 0 and 1 is linearly divided, equally divided into 5 values. So let me show you an example. You see it goes from 0 to 1, and then every element in between is equally spaced from each other. And you have torch.arrange. This will just start counting. It will not divide the space linear, it will just start counting the integers. So let's say we want to go from 0 to 10, and the step is 2. So we go 0, 2, 4, 6, 8, but 10 is excluded in arrange, okay? In linspace, it is included, but in arrange, it is excluded. And one last thing for PyTorch, you can say torch.empty and create a matrix. So this will just occupy memory, initialize like, so okay, so this matrix will be in this memory, but it will not change any values. So whatever numbers, random stuff, information was in the memory, it will remain. So this is initialized tensor, contains garbage values. In this case, it seems like all of them are 0 for some reason, but maybe they are like very small numbers, like 0.0001 or something. They may be like some random values close to 0. But be careful, you cannot use this. You need to set some actual values when you create an empty tensor. So that's gonna be it for PyTorch module, and let's go to next module. Now let's go to neural networks. So usually we have some input. In this case, it's an array of 3 numbers, or a tensor of 3 numbers. We have this number, and this number. Here in this image, it's kind of showing like xn. It means like like until any number. But let's say we just have 3. And the first one will be multiplied with some weight, which is also some number. Second one will have its own second weight, multiplying with that. And third one will have its own weight. And so the goal for neural network is to learn which these weights should be, what numbers they should be. So if we have some input, it will create correct output here. So let's say this is input of an image of a dog, and the label should be dog. So how do we multiply this input with what numbers, what weights to get like the correct label? And we have an architecture of the neural network designed for this. I know that might be a bit confusing, so I'll just continue explaining a few times so you will understand it. So each of the input numbers has its own weight, so it's multiplied, and then they are all added at the end. So multiply these two plus these two multiplied plus these two multiplied. So you get one number at the end. And that number should correspond, for example, if we say like number 1 means cat, number 2 means dog. If this input is image of a dog, then these weights should be learned by neural network such that this at the end gives number 2 for the dog, if this is input dog. Or if this is picture of a cat, at the end it should give number 1. So how does neural network needs to learn these weights? So it gives like 1 or 2 based on if this is picture of cat or dog. And these weights are always the same, they're not gonna change. If that's a bit confusing, let's try again. So inputs, in this case, we just have 2 numbers, and the weights are also some numbers, and this is learned by neural network, but let's now just give these examples. And first of all, we multiply first weight and first input plus second weight and second input. And at the end, we can also have bias. Bias is like a number. It's also learned by neural network. It just added to all of these input times weights, all of them. So it's just one number. It's not separate for every input. It's not separate for every weight, just one number. So when you add some number, look, first of all, this input times weights, this will approximate some function. And when you add some number to the function expression, it will shift function left or right. So imagine you have coordinate system, you have some function. if you suddenly add some number to that entire function, it will just move the function left or right. So that's why like this bias is there. But you don't need to actually use the bias. You may or may not use it. I know at first these neural networks seem very complex, but with time you will understand everything I'm talking about. So don't worry, don't despair, don't get overwhelmed. Let's just continue. So this is our example that I was explaining. And we see we have this 0.3 number. And it's a bit weird because it's showing this like long number, 0. I don't know why it's showing this long number. Is it some like bug or the way Python stores numbers? But it should be just 0.3. And it's called weighted sum because you weighted sum because these are the weights. You add inputs 2 plus 3, but first you multiply them with weights. So how much do you weight this input? How much do you weight this input? And then add bias. Okay, so the weighted sum is 2, and we may actually have some non-linearity. So when you just add and multiply, you're gonna get a linear function. If you wanna maybe curve this function, so let's say you have some data here, you have some data everywhere around. In order to separate them, you need like a curved function that separates this data. So activation function will curve our function here. Again, like we have a whole module. We will understand activation functions again, like in detail. So like I know this might be difficult, but just try to like follow as much as you can. So activation function, you see this is one of them, sigmoid, and whatever number you put in on this, so that number will be on x-axis. Whatever number you put in, it will squish. It will output number between 0 and 1. And you see how it has this curve. So that's the way you can curve your function that's actually approximating, that neural network is approximating. You know, neural networks are approximating functions. But adding and multiplying will only approximate linear functions. So you need also activation to be able to curve the function that neural network is trying to approximate. So you see here we put number 2 into sigmoid and it gives 0.88. So I said it will always give number between 0 and 1. And it's actually good because in neural networks you want to have numbers between 0 and 1, minus 1. You don't want to have numbers minus 100, minus 1000, because once you start multiplying those numbers, because those numbers will get multiplied later, then it can explode. You will start having like huge numbers that cannot fit in memory even, or that cannot be represented by FP32, by FP16, etc. So you want to keep your numbers nice around 1, around minus 1, and these kind of numbers. You don't want to keep them even too small, because when you start multiplying very small numbers, they will become a lot smaller very fast, and then you cannot represent those numbers either. So numbers around 1 will kind of tend to stay the same, around 1 as well. And then you occasionally normalize, you occasionally push them towards 1. So push down or push up towards 1. That's what normalization is used for, to keep them from exploding or diminishing. We can write some code now. So class neuron, we're gonna initialize a neuron. It's gonna receive number of inputs. And weights are gonna be same number of weights as number of inputs, because we need to multiply each input with the weight. And we will initialize weights at some random numbers. We don't want to initialize weights at 0, because when we multiply inputs with 0, we will just get all zeros. And then we want to maybe scale down the weights once we initialize them. So maybe that's what people do. Maybe it works better. And then initialize bias at 0, because we are adding bias. That's okay. We're not gonna ruin like inputs, because we are just adding 0. We would ruin like everything if we multiply with 0, but adding 0 will not ruin the inputs. And here I can instantiate this class neuron, pass in number of inputs 2. And so we can just say neuron.weights and neuron.bias. So neuron.weights, these are initialized weights, and bias is 0, and that's how we initialized it. Now there are better ways to initialize weights, like chiming or some other, but we'll talk about that later. Next, I'm gonna add this part of code. So the class is same, everything is same. I'm just gonna add this weighted sum. So I can use torch.dot, which will just do the dot product between weights and inputs. It will also do matrix multiplication if these are matrices. So right now they are just 1D vectors, so they are just vectors. Okay, so that's how you do the dot product and add bias instead of manually adding each element and stuff. So we had this part of code already, I explained it, initializing, and now we want to add some input tensor and pass in. So through the weighted sum, pass in inputs through the weighted sum. This is going to calculate the result. And usually this weighted sum is actually called forward, not a weighted sum. So later we will call it just forward. And this is what we get. This is our weighted sum. And let's add activation function. So again, all of this is same. And now we add new sigmoid. So this is formula for sigmoid. So 1 over 1 plus e to minus x. That's the formula for sigmoid. This is the function that I explained that squishes between 0 and 1. That's just the formula. There is nothing to know about it too much. And so we already did this part, and now we add this part. So we pass our weighted sum through the sigmoid. And then, as I explained previously, weighted sum can only be this function, but now it can be curved in whatever like way based on these numbers that get in. And now to make it more standard, I'm actually gonna rename this or call this forward. This is in the next cell, so you can still like go back and check what we did here. I created a new cell, and now I'm calling it forward. So I do weighted sum and I pass through sigmoid and return the output. So that's the forward of this neuron. And I define sigmoid here. And that's it. And we can test with different inputs. So this is for you to play around. And so for input in test inputs, we're just gonna do forward every time and see that depending on the input, this is the weighted sum, this is the sigmoid output. And also we can have different activation functions. So sigmoid, relu, tanh, all of them look kind of differently. Relu is very simple. All numbers that are less than 0 or 0, it will just convert to 0. And all numbers that are greater than 0 will remain the same number. It's very easy to calculate, it's very fast on computer, but it's simple, it may not be so powerful. So this is when you need some simple task in the neural network or large language model. So you see here, relu is torch.maximum of 0 and input. So if 0 is greater, it will be 0. If input is greater, it will just be the input itself. And tanh function, this will squish any input x between -1 and 1. So sigmoid is between 0 and 1, and tanh is between -1 and 1. But we will talk more about this later. So now in the forward pass, I would call this activate. And I believe I was in the initialization, I chose which activation function I would use. And so here we can just try different activation functions. And let's see different results. So sigmoid, relu, tanh, linear. I guess linear would just be whatever gets in also gets out. I think that's all you need to know. You don't need to like even understand. So even if you didn't understand what I just said, we'll talk about this later as well. So don't worry. Now let's connect multiple of those neurons into a layer. Because one neuron can just represent maybe like this function. It's a bit curved, okay? But when you add two neurons, now you can represent like two bending points, two sigmoids. So now it's more complex. Now you can maybe encircle more data or more precisely, or you can do more things because now you have two bending points if you have two neurons. So here we would still have same input, but we would have two neurons. So weights for neuron 1, weights for neuron 2. So it would multiply input with these weights to get neuron 1 and multiply input with these weights to get neuron 2. And we have two biases because we have two neurons. So did I run all of this? So you can just use matrix multiplication to multiply this all at once. Like this, so input times weights transpose. You need to keep in mind how matrix multiplication works. Because we have this row, we need to multiply this row and this row, but matrix multiplications will not multiply two rows. It will multiply row and a column. So you need to transpose this to turn this into a column. This is just how matrix multiplication works, so keep track of that. And now the outputs will be an array of two numbers, two neurons, and we can pass that array or tensor through torch.sigmoid, and it will automatically do them one by one separately. So you see, this is the output, 2, 1.8, and when we pass that through sigmoid, it will just do separately each of them. I think I can go a bit faster now. So now let's create a class layer. So it's gonna take number of inputs and number of neurons. They don't need to be same numbers. So you can have 2 inputs and 3 neurons. So we will initialize weights, initialize bias. This is the same. Create sigmoid. This is all same. Forward pass. We'll do the matrix multiplication and add bias, and then pass through sigmoid, and that's it. I think it's very, like, we just explained this as well, so it's very simple. And we can say 2 inputs, 3 neurons, and in this case we are, even though we initialize them randomly, here I'm overwriting the weights and I'm overwriting the bias. So you can say layer.weights, layer.biases, and then inputs. I'm actually setting which inputs I'm using and then passing those inputs through the forward. And this is the same as we just explained, so I think it will be easy to understand. Interestingly enough, you don't need to pass just one input. You can pass multiple inputs at once. So you can create an array of inputs and pass all of them through the forward, and it will work. Because this matrix multiplication in forward pass will notice that now inputs has one more dimension. It's called batch dimension, but it will still take every input and matrix multiply with this. So now at the end it will just produce the batch of outputs, array of outputs instead of just one output. So it will work automatically. And it will automatically apply the sigmoid properly to each output in the array. Let's see activation functions. We already talked a little bit about them. So I got a bunch of math. This is just, you see you have input x multiplying by first weight, multiplying them by second weight. This is just what we were explaining about weights. But because it's just multiplication, it's gonna be a linear function. Whatever, like the function of this w and x will be linear. But if you have some activation function that activates inside here this first weight times x, then this activation function may not be linear. So that's how you can, like if you have like some data, you can encircle it, create a boundary between this data and this data. So sigmoid, it's just the formula. We already explained this. This is the sigmoid between 0 and 1. And this is the derivative of sigmoid. It's just good to look, but I don't know if this is useful at all, so it's just good to look at. We got hyperbolic tangent, the formula and all this good stuff. So between -1 and 1, it's just good to remember this, but it's okay even if you don't remember it immediately. ReLU, this is good for simple processing, so if x is smaller than 1, it will be put to 0. If x is greater than 1, it will remain x. Derivative is like this. Leaky ReLU. So this is maximum between 0.01 times x and x. You see now it's kind of leaking a little bit. So the advantage here is it doesn't just lose information if x is less than 0. Okay, there are like more functions. You would usually use a sigmoid or tan age or something like that. You will eventually dive deeper into this. This is just beginning. So for now, you don't need to worry about it too much. And this is a good example. You see straight line if you just multiply and add. And then if you add activation function, you can separate this data better. Then we have this SILU function, which is popular. So it's similar to ReLU, but it also doesn't lose all of the data if it's greater, if it's a little bit less than 0, but eventually it will converge to ReLU. So this is actually useful. This works better with neural networks. It's a bit harder to calculate than ReLU. So ReLU, if you have some simpler task, it may work better. This is the formula for SILU or swish. So it's x times sigmoid of x. And we can go down and implement it. So you see ReLU and SILU. You see that SILU is a little bit curving around ReLU, so it doesn't lose information here, but eventually it's going to converge to ReLU. The main advantage here is, imagine you have some data, and ReLU, it's like a sharp corner, but swish or SILU, it gives you like a bit more curve, so you can better circle the data. I can show you a bunch of these functions, what they look like. This is just fun to watch, but you don't need to memorize this right now. I just like checking them out. Let's talk about loss. So when we're training a neural network, we have some inputs. We want it to produce some outputs. So it's gonna learn to change weights inside that multiply inputs so it gets correct outputs. Now, how do we know if the output is correct? We use the loss function. Loss function is error. It's the difference between the predicted output and the correct output. And we can use mean square error as one of the loss functions. So it's predicted output minus correct output, and then square that. Let's show this on an example. We have predicted output, maybe predicted numbers, and true numbers, true output that should be here. And so first of all, we will subtract 2.5 minus 3. That's going to be our first number. And then 0 minus 5. And so we subtract each of these individually. It's like subtracting vectors. And then we square each of them. Like now we get resulting vector, and then we square each of these numbers individually. Once we square them, we find their mean. So imagine it like this. First we find error by subtracting. Then we square the error, which will... So we do that because if error is big, the square of the error will be even bigger. You know, the bigger the error, the square will be even bigger. So we do this to punish big errors, because we will increase big errors by a lot, and small errors will not be increased so much by squaring them. And then just find mean. I could say maybe average of all of those numbers, all of those errors, by just adding all of these numbers and then dividing by the amount of them. We also have cross entropy loss. This is used when you have some classes like cat, dog, bird. This is also used in large language model because large language model is selecting out of all of the possible tokens or words or tokens the next word, the next token. So it's also like you have classes. Each token or each word is a class to select one of them. Let's see some example. Let's say 0 means cat, 1 means dog, 2 means bird. And so if we get this tensor 2, 1, 0.1, here the biggest number is 2. So neural network is most certain that it's predicting cat here. Because cat is highest, here is predicting dog, here it's also predicting cat, and here it's very certain 4, 0, 0. But check this out. The correct solution is cat, dog, and bird. Okay, so cat, this is correct. Dog, this is correct. But here it should have been bird. But the neural network was wrong here. And we can just call this nn.cross-entropy loss. And then that's how we initialize it. So criterion is equal to cross-entropy loss. And then we can pass logits, which is what neural network calculated, and targets, which is the correct solution. And it will give us some number at the end, and the worse the prediction, the higher this number will be. I changed the notebook just now, so let's understand cross-entropy a bit deeper. And so first we need to create probabilities from the logits. So if you have these numbers, logits 2, 1, 0.1, we need to convert these to probabilities, to percentages. So they all need to add up to 1, to 100%. But keep the relative sizes same. And one way to convert any numbers into actual probabilities is you can exponentiate all of them, and then each of them you divide by the sum of those exponents. You exponentiate to make them positive because probabilities are cannot be negative. So this is one way to do it. You can do it in different ways as well. And I'm not sure if exponentiate is correct term. I mean like you put e to this, because x is gonna say e to this. So each of these will be e to 2, e to 1, e to 0.1, which is Euler's number. And this is step by step. It has this array, and if you put e to each of the numbers, you get this sum. And then after dividing each of them with the sum, you get these numbers which add up to 1. So you can then look at them as probabilities. Probability is a cat, it's 65%, etc. And this is what cross-entropy will do. If model predicts correctly with high confidence, then loss is low. So if its prediction is correct and it's very confident, meaning it gives high probability to the correct prediction, correct answer, then the loss is low. So these are the logits from the beginning, and our target class is 0, which is cat, which is this one. And here we can see we only look at the probability of the cat, only look at that probability, and then we calculate this minus negative log of the probability. So this is also called negative log likelihood. And the higher number you put here, the lower number will be here. This is how it works. So if the confidence here is high, then the error will be smaller. If you are curious, you can ask ChatGPT. It's not obligatory, but you could ask ChatGPT and see why and how this transforms this number. Now let's see wrong prediction. Let's say the correct one is this one, but it assigns 0 to that one. So if we calculate probabilities again, let me show you here. First of all, the probabilities will not be 0 here due to the fact that we are exponentiating So e to 0 will still be e, so it will still be 2.7 something. So the way we calculate these probabilities, it will not be 0 here, but it will be a very small number. And then see what happens. Negative log of very small number, it's gonna give us very big number. So now loss is very big. It's 4 point something. Previously it was 0.4, it was very small. Again, you may copy any of this code and try to understand it deeper, but I'm gonna go on because that's not necessary, but you will eventually understand this, especially if you wanna do some research on this stuff. Let's draw this image. Let's see how this loss behaves. So if we have high confidence, high probability for the wrong answer, then the loss will go very high. And I think the loss will keep like converging, like it will start growing exponentially. And if it's a high confidence into correct answer, then the loss will go towards 0. You can also do batch cross entropy, which is just calculating a bunch of cross entropies at once. I'm gonna skip this example. It's you don't need to, actually it's not so common. And why not use just accuracy? So why don't we just use if the answer is right or wrong? And why do we need to calculate this number, these probabilities? That's because it's differentiable. So it's a smooth curve where you know if you increase this weight, the loss will get higher, the loss will get lower, okay? But if I was just to use true or false, correct or wrong, then if I increase this weight, I don't really know if it's gonna, like, if it's actually becoming more true or more false. If I keep increasing, maybe it will suddenly snap to true or snap to false. But I want it to be differentiable. So I want to, if I increase this weight, change neural network a little bit, I want to see if it's becoming more true or more false. What is the probabilities and the loss? Let's go to backpropagation from scratch. This is how neural networks learn. Now, this is a bit tough, and also you would usually not care about this in PyTorch. This is done automatically. But we can quickly go through this. So let's first check our forward pass, which is multiplying weight times input plus bias. And in this case, we just have one neuron to make it simple. And then we will pass that output through some activation function. Let's just say it's gonna be equal. It's gonna be also z. So to make it simple. And then loss, we calculate the error. So predicted minus true and then squared. That's one way to calculate the error. We just have one neuron, one number, so this is the easiest way. What backpropagation will do is we want to see if I change this weight and bias, because we are changing weight and bias. How does loss change? So I want to change weight and bias. So that's how neural network is learning. So the loss becomes smaller, goes down. And you can calculate that using gradients and derivatives. I told you earlier that if you have some function like this function or whatever function, you can, by calculating gradient, you can see in which direction it will go down. That function the value will go down. So if we have a loss function, by calculating gradient with respect to this w, we know that if we change w, does the loss go down? Or if we increase w, does the loss go up? If we decrease, it will go down. It can also happen that if we decrease w, the loss will go up. So it can, like, anything can happen, but we need to calculate what's gonna happen. Should we increase or decrease this number, w, for the loss to go down? And for that, we will use the chain rule. So starting from the loss function, we can go back all of these functions to get to w. So it's like calculating gradient of the w. So I'll try to explain this chain rule a little bit. So I think this is just theory. You will not use this. Maybe you will use this when you become like very good at research. But let me just quickly go through this. So first we have this loss function. So first we start by calculating how does loss change if we change this predicted w because that's our variable. This predicted W is our variable that's dependent on our W and B. This true will not change, this is constant. So first we calculate how does loss change if we change this predicted. Okay? And then how does this predicted change if we change the Z? And then how does Z change if we change W and if we change B? So you see, it's like a chain rule. So that's how we can get, when we change W, how does L change? By going backward. Okay, I think that's gonna be it for backpropagation. This is the whole thing here. I can put it together. So I wanna see how does loss change if I change W. So how does this loss change if I change W? Do I need to increase or decrease W to decrease loss? And so the chain rule is the following. How does loss change if we change predicted W? How does predicted W change if we change Z? And how does Z change if we change the weight? That's the chain rule. And so I just put all of the numbers here. I calculate the derivatives and stuff. Okay, but I think that's, I just want you to understand like the chain rule, how you go backward. I have some code here to calculate it manually, but I will go quickly. Maybe we will not do this right now. You can do this yourself if you want. You can talk to ChatGPT or you can watch my video, Backpropagation from Scratch. The reason I'm gonna skip this is a bit complicated and it's not so useful for our current large language model because this is all abstracted away. But just the important thing is we are defining torch tensor and we're gonna say requires gradients to true. So this is how we will be able to calculate backpropagation automatically with PyTorch. So we wanted to keep gradients and we have like some input, some correct output, and then we have some forward pass. So Z is equal to this, and then Y predicted will just be Z, and then loss is Y predicted minus Y true squared. And then I do the manual back. So first I find the derivative of this, which in the derivation rules I said you put this exponent in front of the thing. Now there are a bit more rules here, but in this case this is just a derivative. And so we're gonna find the derivative of Y predicted with respect to Z, which is just gonna be 1. Okay, let me go quickly through this. Then when we have all of those derivatives, we just multiply them. In the end, we will get this. So in the end, this means if we increase W by 1, loss will go down by 18. If we increase weight by 1, loss will go down by 6, which is very good. These are very steep gradients. And then PyTorch automatically calculates the same thing, which means our implementation is correct. So you may or may not look into this deeper. And let's see how we build linear layer with backpropagation. Initializing weights and biases. And remember, I didn't mention this. So this is how you would initialize weights. This is the number of neurons. This is the number of inputs. And this way, you already transpose the weight matrix. We'll see later, but this is, just remember, number of neurons, number of inputs. And we want to store some gradients, so I'm manually cache for backward pass. We'll see. Store input for backward pass because this derivative of loss with respect to W depends on X. And this is the forward pass. And then the backward pass. The same thing. Actually, we don't need to look at this. Is the same thing that I just did. We can code this whole neural network from scratch. So we defined all of this manually that I was just showing above. And so if we define all of the training loop here, which we will talk about later, I just want to show you how first loss is very big and then loss goes down, down, down very fast. And then weights start from these numbers and then weights go to these numbers in order to make the loss very small. And you see how target loss is actually going down. So we coded this manually, you can take a look, but let's go on to the next thing. Now let's talk about the training loop itself. Training loop has forward pass, computing loss, backward pass to calculate how do we change weights. If we change weights this way, how does loss change, how to make loss small. And then optimizer step is actually changing the weights. And now that we change the weights, the loss is going to be smaller. So now we go back to the forward pass again. We repeat this cycle. Every time we change weights a little bit to make the loss smaller, to make the error smaller. And later, so okay, let's see. Now instead of coding the layer manually, we will just use the built-in layer by the PyTorch. We can also use built-in mean square error loss and stochastic gradient descent. With this learning rate, I'll show you what learning rate does. Okay, 100 epochs means we are going 100 times over data. We'll see. So for each epoch, we will first zero out gradients. So, you know, when we update, when we are here, we update the weights. When we go back to the beginning, we want to remove all of the information about the gradients because now we're going to calculate new gradients again to see what the loss is and how to change weights. So it's like cleaning the memory. By default, it's not cleaning because it helps with some type of neural networks like RNNs where you don't want to clean them. But don't forget to always clean this by default. And then when you have your model, you would just do the forward pass by passing input through the model, and that will give you Y predicted. So our model is just a linear function in this case, just a linear single linear layer. And then loss is based on the predicted and Y. This is our cross entropy loss. And in this case, I'm just gonna save losses so I can show you later, but you don't need to save losses. And then do loss.backward to calculate how do we change weights to make loss smaller, and then optimizer step. This will update the weights. So I didn't run this, let me run this. And you see here I'm just typing every 10th epoch, not every epoch. In the beginning, loss is very big, and then loss starts to fall exponentially. If loss is starting to increase all of a sudden, then you have some issues like overfitting on training data, but we'll talk about this later. Because our task was very simple, you can see that loss goes down very quickly, and then we don't even need to train so much here. Like we can just cut it here. This has learned enough. And here it's very simple. We have all of this data, and we want to try to predict data. And here, because we don't even have activation function, we just have a linear layer. So this red line is like the best prediction for all of the data points. If you know the way we generated this data, if you go on top, we actually just did 2 times x plus 1. This is our function. And then added a bit of noise to push it a bit left, right, everywhere. So that's how we generated this data. And then the neural network learned, but neural network does not have any curves. So neural network linear layer, we don't have activation function, so it can just predict a line here. Also, when testing the model, use with torch no grad because you don't want to generate gradients. It's unnecessary when you are testing using the model. You only need gradients when you are training the model. Let's look at this most famous optimizer, Adam Optimizer. I have a video here if you want to watch. It's more detailed, but now I'm gonna go a bit quicker. I don't want to make this course too complicated, but you may watch my video here now or another time. It's this video. Adam Optimizer explains step by step, first and second moment, zero bias correction. Stochastic gradient descent versus Adam. So first of all, I told you that when you have weight, like some number weight, calculating gradient will tell you how to increase the loss remember, we want to decrease the loss, but gradient will tell you how to increase the loss. So gradient will tell you if you increase this weight, then loss will increase, or if you decrease this weight, the loss will increase, okay? So whatever the gradient is, this is the gradient here, delta L of, so delta L with respect to weight, that's our gradient. So if we add this gradient to the weight, the loss will increase. So we want to subtract this gradient from the weight to decrease the loss. And that's kind of funny because not only, so because gradient is telling us how to increase, we can literally subtract the gradient itself or add the gradient itself. We can kind of use it, it's like a trick. But these gradient vectors, they're gonna be very big numbers. So we actually wanna multiply this gradient with a very small number, 0.01 for example. Because we wanna subtract very small number. We don't wanna subtract gradient is too big. So we multiply gradient with very small number, 0.01, and then subtract that, and that will reduce the loss. Now this is called learning rate, and learning rate is the most important hyperparameter, so you should test out different learning rates to find the best ones for your setup. Usually it's 0.01 for Adam, but it can be 0.07, 0.007. It can be like depending on your neural network. You need to test out different ones to see which one learns faster. This is the problem with stochastic gradient descent. Look at this loss surface. It's very messy. So when you move through this loss surface, the gradient will start to point like this that way, and then this way, this way, this way, this way, this way. So the gradient is always gonna show you like where to move. But because the surface is very messy, it's gonna be like a bit random. So we wanna utilize momentum. If we are consistently moving like this, and suddenly it shows like this, we wanna actually keep moving this way, because these random oscillations, it may be just a bunch of randomness because the surface is so weird. So we want to keep the like a bit of momentum going on to neutralize this randomness. We don't want to just follow the randomness. And then we also want to kind of make equal amount of steps. So if suddenly gradient gets very small, which would cause our steps to be very small, because as I told you, gradient is proportional to the steepness. So the steeper the thing, the larger the gradient. So it's good that the gradient is showing us where to go, but we want to always keep making same steps or equal size steps, because if the steepness is very small, then gradient will be very low. So we want to increase, stretch the gradient if it's very low. Or if it's very steep, the gradient will be huge, but we don't want to make huge steps, because we might end up somewhere else. We don't know where we will end up. So we wanna, if it's huge gradient, we wanna squish it back. So that's what this variance, the second momentum, will do. It's gonna try to make steps all equal size and not so dependent on the steepness of the lost surface. Let me check conclusion, because it has very good points. So stochastic gradient descent takes small steps in this case and struggles to navigate curved valley. It's slow, but Adam keeps momentum and first and second momentum for every weight individually. So no weight is gonna start changing very slowly or too fast, and which can be unstable, which we don't know what's gonna happen. And here there is a comparison between the green, which is Adam, and blue, which is stochastic gradient descent. You see they take different, starting from here, they take different paths on the lost surface, and Adam will just be faster, it will converge faster, it will take larger steps. So Adam will actually find faster, better path. You don't necessarily see that on this image, but trust me, bro. We also have a Muon Optimizer, the next lesson, which is better than Adam, but it only works on 2D matrices, so weight matrices. So you cannot use Muon for vector embeddings or some other things, only for 2D matrices. The thing with Muon Optimizer is these people who invented it figured out that if you keep update matrices and weight matrices, these weight matrices in neural networks, orthonormal, which means if you look at first row and then second row and then third row, if you look at them as separate vectors, if those vectors are orthogonal to each other, then the neural network will learn faster. Now, I'm not sure if they understand why it's going to learn faster. I'll try to understand it, but I don't know if anybody understands it. But this is the thing. We want to keep weight matrices orthonormal. So rows are normal to each other or columns are normal to each other if you look at them as vectors. Usually you would need to calculate singular value decomposition of the matrix, but that's very slow. So they found algorithm to make matrices orthonormal a lot faster. But first I wanna just say that they keep the weight matrices orthonormal by applying that algorithm to weight update matrices, so to gradients. You know, optimizer will want to add some gradients to the weights. So, you know, weight minus learning rate times gradients, which I just explained earlier. And so if you keep that weight update, the gradients orthonormal, then every time you add them or subtract them from weights, the weights will also by default remain orthonormal because you're adding orthonormal matrices always. Okay, this is a bit tough, I know. Muon Optimizer, it took me like a month to understand it. I have some videos on it as well. So I guess let's not spend too much time. The purpose of this video is to train large language model, and we will train it just by like copy pasting Muon Optimizer, which I also did. If you want to do research on Muon Optimizer, then you can understand it deeper, but it's gonna take some time to understand it. So here, this is the approximation of the singular value decomposition and orthonormalizing the matrix. So G is our gradients. It's also the weight update matrix. We use gradients to subtract gradients from weights. And we want to make this matrix G orthonormal. So first we will start with these coefficients. And you will see that this looks like a polynomial approximation of this process, orthonormalization process. And so we will make this G almost close to orthonormal. We will not make them perfectly orthonormal, but neural networks can handle that. It doesn't matter then. And so this is the algorithm here. First of all, X is our weight matrix, but in half precision. So that's FP16. And so first we will say A is equal to X times X transposed. And you will see here that this looks like a polynomial because this looks like a squared times some constant C. You see the constant C, constant B, constant A. And then A times B, which is also like this is variable, this is variable squared, so it looks like a polynomial. And then you multiply X, which is our gradient, with this B plus constant A times X. So imagine it as if this is changing X, it's making it more orthonormal, and this is keeping the old X. So we want to keep the old X as well. We don't want to change it too much. So we keep the old X and we also change it. So that's the new X. And we do this 5 times in this case. Every time we do this resulting X will be a bit more orthonormal. So we just loop 5 times. Like here, this is where we loop. Every time X will be a bit more orthonormal. You can also try 10 times, but 5 times is enough. So we want to do it also fast. This is just if the matrix is wide, has more rows than columns, we want to make it, if matrix is tall, we want to make it wide because it learns faster. The numbers are, this is a bit tough to understand as well. I think I explained this in the videos, but it's not so important for now. And the important thing with Muon Optimizer is you only wanna pick matrices that are 2D matrices. So you only want to optimize 2D matrices with Muon Optimizer. And it's also using this momentum. You can use Nesterov momentum or not. Usually they are using. And it's similar to other optimizers. Now I have some notebooks here if you wish, but I'm just gonna go over this one, learning rate scheduler. This is important, and others are good if you are curious. Learning rate determines how much we update weights. So you multiply gradients with learning rate. And here you can see that during the training, we can actually reduce slowly the learning rate. The logic behind this is in the beginning, where it doesn't know anything, we want it to learn more. But as it becomes smarter, the neural network, we don't want to modify weights too much, because it already knows, and now modifying weights too much might actually ruin the things. In the beginning, modify more weights to learn, but later modify less and less because it already knows and we don't want to ruin what it knows. In large language models, it may actually look something like this, because at the pure beginning, it doesn't know anything, so the gradients will be random, but it will quickly learn, and then because it quickly learns, as soon as it trains a little bit, it will have better gradients, it will learn more, so now we want to let it modify more, and then the same rule later, it knows more, so we don't want to change too much. Here are some examples of learning rate schedulers. So you have a step learning rate. It's like this. For a bit, you do this for 10 epochs, 20 epochs, 30 epochs. Cosine annealing. This is actually most common one, I think. It looks like cosine. And you would define this scheduler to be equal to optimizer.learningrateschedule.step learning rate, or whatever your learning rate is. And then you pass in the parameters. And that's it. I think it's very simple. Now let's go to transformers. So transformer, like large language models, it looks like this. You may have seen this before. So we have input sequence. So let's imagine this is large language model like ChatGPT. So we have sequence of words, which is actually a sequence of tokens. They're not necessarily words. They can be half of the word or part of the word. But each token, part of the word, is converted to some vector embedding. It's like a vector, and each vector, I can explain it here better. So the dog ran quickly around the, so each of them will have some numbers, and then these numbers encode the meaning of this word, the. That's what this word means. So neural network will figure out how to, what numbers to put here to encode the meaning. First of all, there are multiple ways you can tokenize the text. So it can be each character is separate token, and then each character would get its vector, and then you pass this vector into the transformer, into the large language model for processing. So if we have text, this is how we build like a tokenizer that's just each character. So we split this text and we just take unique characters from it, and then we map the character to a number, because we're gonna always map each token, is it character, word, subword, to number, and that's how we map to numbers. And so we will have these dictionaries. So dictionary, string to integer, integer to string. So this is encoding for, and then this is for decoding, to converting back, list of integers to characters. So if I have a word hello, and then it's gonna be decoded like this. It's 4, 9, 12, 12, 13. Those are the vocabulary indices of these letters. I can decode it back. And so we will use this to process, to put it for neural networks, for the large language model. And this is explained in Andrei Karpathy's video, GPT from scratch, but I will go over it here as well. The problem here is you have so many tokens, and each of these needs to be processed separately. For 5 letters, you have 5 tokens, okay? But if this whole thing was 1 token, then you would just have 1 token. You would just need to process 1 vector with your LLM. Or if it was 2 tokens, maybe like this and this, then you would just need to process 2 vectors. But here you have 5. So that's the problem with encoding each character as a token. Although I do believe eventually we will encode every character as token as we figure out how to do it better. But right now, the current architecture is not good with too many tokens, too big sequences. So our tokenizer will actually be a byte pair tokenizer with byte pair encoding. Let's say we have some text, low, 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 lower, newest. I want to show you this because you see, you have a lot of times this low, word low. So it would make sense to put this into a separate token, because then you would save up a lot of compute. You can replace all of these with just 1 token. So you would save up a lot of compute. You would bunch up a bunch of tokens into one. So first we will split manually everything into words. And we do the splitting into words here, and then this will split into characters. So every word will be split into characters. And this is what it would look like. So this is the word split into characters, word split into characters, and this /w shows the end of the word. And then we want to merge most frequently occurring pairs of characters, or 3 characters, or 4 characters. So the more frequently it occurs, the better it is to merge, because we will condense all of that into just like token, token, token. So the more frequent something is, the better it is to put that whole thing into a single token. We will do a lot of compression there. And I don't mean this whole thing into a single token, these 3 words. I just mean like this word into a single token. And when we are converting 4 characters into just 1 character, 1 token. So then, because it's so frequent, we automatically get so many of these characters condensed and compressed. So in the next step, we will just count pairs of letters. So letters next to each other. You will notice that L and O are most frequent pair in this first counting. The first time we count pairs, L, O are most frequent. Looks like OW is as frequent. So in that case, we would just pick one, maybe the first one we counted, and then we can merge them into same token. Look below. Now we merged LO into same string here. So by merging that, we made a number of these strings, number of these tokens a lot fewer. And then you would just repeat this process. Now you would look at these pairs and try to figure out most frequent. You see that we have LO and W, LO and W, LO and W, LO and W. So that would be our next merge. Those are most common. Also, we have W and end of sequence W, but those are just 3. So LO and W are most common. So now we merge those, and then that will do a lot of compression next. Okay, so that's how we just repeat this process until we get, for example, 300,000 tokens or 200,000 tokens. And after that, we don't want to get too many of them, because we still need to do probability distribution across this entire vocabulary. So probability distribution across all of the 200,000 tokens. So we don't want to have too big vocabulary, because it will be very difficult to calculate probability. It will require a lot of compute. So we need to find the balance between size of the vocabulary and compression of the sequence, reducing the sequence length, because here this is how we reduce the sequence length, by combining, creating new vocabulary. As I said, so this gives us balance between sequence length and vocabulary size. Because if either of them is too big, then the compute necessary, it will cause some problems where it will require too much compute somewhere in the large language model. But usually we would just use pre-trained tokenizer, and I'm using pre-trained, pre-built tokenizer in my large language model. And this tokenizer is good for small language models. So I'm just gonna install this library transformers and import auto tokenizer, and then say from pre-trained import this tokenizer, it will download it. And then we can check the vocabulary size is 49,000, etc. And if we have this sentence, I can tokenize it. These are the tokens. And so these are the IDs of tokens. And looks like each word is its own token in this case, which doesn't have to necessarily be, especially if I use some complex word, maybe like auxiliary. Maybe that would actually be split into multiple tokens, because if it's not too frequent. So that's it for tokens. You can always watch some other videos on YouTube, but for now this is all you need to know for training our large language model, just how to use this pre-trained tokenizer. If you want to do research on tokenizers, then you may even understand how to build one. And then loading data for your large language model or for wherever. We could, so this is some dummy data that I'm generating. You could always generate dummy data, but in the real world, you would download real data. And remember, this is data generator, and I use this yield. So yield is a bit different than just a for loop, because yield lets us stop. Like for loop, when you trigger it, it's gonna go. But here, this is like a for loop generating data, but I need to call it manually to do the next iteration. So it gives me like more control over how much I wanna do it. So this is called a generator. So you would download the tokenizer, download the data, or generate the data, and then tokenize the data. So your text will be split into tokens based on the tokenizer. It's better if I show you down here. So let's go to the third one, PyTorch data loader. And this is the dataset that I will load. A small LM corpus. This is very good for small language models. And this is the dataset within this corpus, because this contains 3 datasets. So I'm gonna choose this one. Streaming means like we don't want to download everything at once, but we will just download the necessary, whatever we want, number of documents. And we will use this data loader to load data, and then convert data to tokens with this tokenizer function, which we defined before here. Here, where we downloaded it, we can just pass the data in. Let's see attention mechanism. This is important in large language models. So let's say we have vector embeddings for token cat, vector embedding for token set and mat. And now let's just take query to be the word embedding on the word cat, and keys to be all of these. Now we want to find the tension between the query, how similar is the word cat to all of these. If we have vector and we want to find similarity with a different vector, how similar they are, this token for cat set mat, we just do the dot product between the vector cat and the vector mat to see how similar they are. So to calculate similarity, we just do this dot product here. And this will do actually the query cat with the entire keys. Keys will be all of them. We took keys to be all of them, this entire matrix. And the query cat will just be this cat element. So we do matrix multiplication. And so similarity between cat and cat is 5, it's very high. Dot product is 5. Cat and set is lower, and cat and mat is even lower. So that's how we find similarity between vectors. And usually a vector will be very similar with itself, so the dot product will be very high. And then we can convert these to probabilities with softmax. I talked about that earlier. So it's gonna be like 76% cat, 17% here, 6% here. Sum should be 1 of these probabilities. Now let's talk more about attention mechanism. So if you have this vector quickly, if you are processing this through large language model, it needs to know what this quickly refers to. Okay, so this quickly refers to ran and the dog. The dog ran quickly, okay? So in large language model, you will have sequence of these vector embeddings for every token. And so you need to somehow enrich this vector embedding that now only represents word quickly with this other context. And we will get enrich with the attention mechanism. So let's look at the vector for the word dog. We will have some weight matrices. We will have 3 of them. We will have for query, for key, and for value. And what these weight matrices will learn, these are learned by the neural network itself. So they will, when you multiply this vector with a query, with the query weight matrix, you will get some query vector. It's different. Query is different from this dog vector, okay? You will also multiply with different key matrix to get the key vector, and value matrix to get the value vector. Now, what are these key query value vectors that you generate from the vector embedding? Let's go back to our original sequence. I said that we need to take context for every of these vectors. We need to also add context what it refers to. But we will only add context from the previous tokens, because we don't want the large language model to add context from the future tokens. It needs to predict future tokens. It shouldn't know what future tokens are, because it needs to generate them, predict them. So only add context from previous tokens. And how? This is how we add context. So for example, this quickly also contains context of the dog ran. So how do we change this vector? So each of these vectors will have its own query key value. So we will generate query key value for each of them. So each of them will be passed through the 3 matrices query key value. And so let's take a look at this quickly vector. It will have its query. And query is a vector that says what it's looking for. So query says, I'm looking for this and this information. And key will say, I contain this and this information. So each of the previous 3 will have its own key explaining what information it contains. And quickly will have its own query explaining what information it's looking for. And we will calculate dot product between the query of quickly and key of ran, and then separately query and key of this, and then query of key of this. So we will calculate dot product between query and each of these keys individually. And the higher the dot product number is, it's a single number, the higher it is, the more this quickly cares about this information that's contained in either of these vectors. So after calculating query and key dot product, we get some numbers, and that shows how much this quickly cares. So for example, it would care a lot about ran, because quickly refers to ran. That's most important piece of information, that it's running quickly. Maybe it would care a bit less about dog, because ran is more important to the word quickly than dog to work quickly. And it would care even less maybe for the word the. That's not so important for the word quickly. The most important one is ren. So query of quickly and key of ren would probably have highest dot product. And then remember, I told you the third thing was the value. So each of these will have value, and we will use values to combine information. So check this out. I said query is what I'm looking for, what information I'm looking for. Key is what information I have. And the value is the actual information that it gives. Now, don't get confused. Value is the information it gives. Key is the description of the information it has. It's different thing. The information it has and the description of the information it has. So that's the key. Key is description. So value is the information it gets. So let's say you have two different value vectors, value of the query and value of the ren. How do you combine information, the value vectors? You just add them. So this is the trick. You need to know this. If you have two vectors, each of the vectors encoding some information, you can add that information by adding the vectors. And now the new vector will hold both of those informations, pieces of information, I should say. So just by adding them. So we will just add value of this plus value of this, and then add value of this plus value of this, and value of this plus value of this. So now we took all of the information. But remember, we calculated scores, query key scores, to show how important each of the information, pieces of information is. So we will not just add the full value vector. We will actually multiply by the score. And let me go back a little bit. I forgot to say. Once you calculate dot products, showing like, okay, this gets maybe number 5, this is most important. This gets 3, less important. This gets 1, even less important. Then you would convert those to probabilities. So maybe this would get 60%, 30%, and 10%. Showing the importance of each of these to this quickly. And then you would calculate, you would multiply the value of this with its 10% and add. And then value of this with this 30% or 0.3 and add. And value of this with 0.6 and add. So that's how you add values, but values are weighted. So each value is multiplied with its importance, with its percentage. So if some value is not so important, it will be multiplied by a very small number, 0.05, and then added, so just a bit of information will be added. And for important values, those will be added more. And remember, we are not operating on these. These are raw vectors. These are vectors of the tokens. We are operating on their values right now. So keys, queries, and values. So value of this will be added to value of this. Value of this will be added to value of this. And okay. So let me kind of repeat on this example again. So let's say we have 3 tokens. And so each of these 3 tokens will have its own queries, a query, and then 3 keys and 3 values for 3 tokens. And then we will multiply queries and keys. We can multiply all at once. So queries times keys. Now you need to be careful. You will probably transpose this key matrix due to how matrix multiplication works. And you would maybe get some numbers like this as a result. And then you need to, okay, this is important. You need to make sure that every token just looks at previous tokens. So for the token we don't want it to look at the future 2 tokens. Dog can only look at the. Ren can look at both of them. So once we multiply queries and keys, we will zero out these points that we don't want them to interact. So the first token can only look at itself, that's okay. But we don't want it to look at the second token, the third token. We don't want it to look at the future tokens. So we'll put zeros here. And the second token, we don't want it to look at the third token, so put 0 here. So this is second token query times first token's key, second token's query times its own key. That's okay. And so if we do, so then when we do softmax, when we find probabilities, we will get that the first token can only look at itself, so it will get 100% affinity with itself. Okay, the second token might look at 55% of the first token and 45% in its own self. So it will get, so this is what we will do. We will multiply first value with 55% and its own value with 45% and then add them. And the third token multiply first value with this, second value with this, and its own value with this, and then add them. That's how you mix blend information, by adding vectors. And by the way, up here is the softmax, how we calculate, how we convert some numbers to percentages. We explained this earlier in softmax activation function. So you put e to the entire array and then divide by the sum of the array. Then you will get each array adding up to 100 or 100% or adding up to 1. So the attention formula is query matrix times key transpose matrix. Now we will actually divide that by the square root of dimensions. So if key matrix has maybe, each key has maybe 300 vectors, we will divide this output with the square root of 300 to keep it stable, so it doesn't explode the numbers and stuff. And then we will do softmax, as I explained, to convert to probabilities, and then we will multiply with the values. So that's the attention formula that we just went over. It's implemented into code here, so scale.product attention, queries keys values, and then math multiply queries and transposed keys last two dimensions, so you don't need to transpose the batch dimension, and then divide by the square root of key dimension to keep it keep the numbers nice and normalized, and then softmax along the last dimension, and then attention weights and values. And so that's gonna give you output, so you can return outputs. In the next lesson, self-attention, I show you how to, usually we would initialize this weight matrix for queries, for keys, for values as linear layers. And so this is the matrix that's gonna convert your token into its key. So input is the token, output is the key, or in this case query, sorry. So query here, this is key, this is value. And in this case, the dimension of the token and the key query value is same. But if the model is big, then dimension of token could be a lot bigger than the dimensions of key query value. But for small models, they're same. So once you initialize these linear layers, you can just generate a query key value by passing x through the matrices. X is the input. Now there is one trick. Usually you would not, you would divide these vectors like query key value into parts, separate parts, each being same size. Those are called heads. And then all of the heads will interact by themselves separately. So let's say we have some query vector of 6 numbers. We will divide it into 2 heads. And then we will multiply this head of the query with this head of the key. And then do this head of the value later. So we would not mix, we would not multiply this head of the query with this head. This is the second head. So we just do same set of heads on the same position. The idea here is like having multiple query key value vectors for each token. Each of them learning different things. For example, maybe first head would add information about history and maths. The second head would process nouns, and others learn some kind of other foreign languages and other information. So it's just like having multiple keys, queries, and values for every token. And they are all done computed separately. In the end, they are all merged into one token again. So maybe for one token, the one head would have this output, the second head would have this output. At the end, we just merge them into a single concatenated tensor vector. And then once we merge them, this will be your value vector. So now imagine for every token, we have a single value vector, and this value vector contains information from previous tokens. So now we are actually back at having one vector for every token, but those are just value vectors. Now we need to convert from value vectors for each token back to the original, like token embeddings. And for that we use this output matrix. So output matrix is also learned. It will just take all of the value vectors that are now enriched with other value vectors from previous tokens and convert them back to token embeddings themselves. Here I explain more theory, like why multiple heads. Head 1 might focus on syntactic relationships, head 2 semantic relationships, head 3 long-range dependencies, etc. So dimension of the model, which is dimension of the token embedding, might be 64, and number of heads might be 8. So each head would then have dimension 8, because there is 8 heads, each having 8 dimensions, so in total it's 64. So the process goes: split query key value into multiple heads, apply attention to each head independently, concatenate all heads once you generate the values, and then apply output projection to convert from values to vector embeddings. Here, as I said, we are defining query key value projection matrices, but we also need output projection matrix that will convert from values back to token embeddings. In forward pass, we generate query key value, and we need to now split all of them into heads. Or we're not splitting, we're just creating a new view. So just adding a new dimension here. So instead of having whole dimension of the entire token or model, we are now just separating into heads, each being its own array. So now we have array of arrays within this. And so we would do the classic dot product attention with all of that. It's gonna stay the same. There is not much here that's changed. We will always like multiply entire matrices, entire sequence of all of the tokens, all of the heads, everything at once. And then at the end, once we are finished, so once we do this like self-attention, we will pass. No, sorry. So first we will convert heads, concatenate them back to just one vector, all of the heads. And now that we have all of these vectors, we will just convert them back to token embeddings with this output projection matrix. Now we can look at the transformer architecture. Input sequence is just our text, and that gets converted into token embedding. And we will normalize the token embedding with RMS norm, make them nice around 1. If they are too small, too big, we're gonna make them around all of the numbers around 1, around 0, -1. So we will not have some numbers in the token vector that are like 100,000. Those are big numbers. We don't want them. After we normalize, we will generate key query value, and then it will go to the multi-head attention. Now, it says here grouped query attention, so which is pretty similar, but we are using the more basic version, multi-head attention, but this is almost the same. So you will be able to easily understand this as well, doesn't matter. And applying rope within the attention mechanism, I'll show you that later. So rope will tell the model where each token is positioned, which token is first, second, third. If you didn't apply rope, then attention mechanism wouldn't know which token is where, the positions. It would just know the semantic meaning of the cat, dog, but it doesn't know like cat is chasing the dog or dog is chasing the cat. So rope encodes the position. after we pass through attention, after we enrich all of the tokens with the context from previous tokens, we will actually add the raw vector of before we process them through attention to these token embeddings that we processed. Now remember, this, let's say a token of vector of token dog. Here it's just gonna be the dog itself. And when we process it through attention, it will also encode previous tokens like brown dog. And now when we add this vector of the dog that also contains information about it being brown to the vector that just contains information about the dog before it was processed with attention, this is the way to keep original information, because that is also valuable to keep. As I said, when we add two vectors, we kind of combine their information. So we will add the process token that contains other information context plus the original token that doesn't contain. So that's how we allow important information to not to get lost. Causal mask just means we are looking at the previous tokens, as I explained, not to the future tokens. And then, so we are at this point, now we still have a sequence of tokens, token embeddings. Now each is enriched with attention. Then we normalize them again. So this is gonna fix if some numbers went very high, like some numbers are 100,000, 50. We wanna keep them around 1, -1, 0, these kind of numbers. And then we will pass them just through simple feed forward. It's just a simple like linear layer. It expands like this linear layer and then goes back, contract. So it's just a simple neural network. And this will process. Now imagine that attention is just collecting information. And then feed forward is processing information, refining, maybe adding more information. So this is blending and collecting, this is processing information. So if we have some vector, if we process this through neural network, it will combine, refine, add more information, maybe because there is like extra facts and knowledge in this neural network, in this feed forward, that might get added. And we also have residual network to preserve some of the previous unprocessed information, if that's necessary for the neural network as well. So it's always good to keep this residual because this may change the information too much. And so that's gonna be one layer of the neural network, and you can go back and repeat. Now go back into this norm again and repeat this any number of times. Usually it's 10 times, 12 times. For bigger models, it can be 36 times, maybe even more for the biggest models. I'm not sure how much they have like for Gemini 3. Maybe they have like 50 or 60 or more. This layer. And after everything finishes, you have very processed sequence of tokens. So you have also same size sequence of tokens, token embeddings. But now they're very processed and they contain a lot of information from previous tokens, and they're very well processed. And you want to generate the next word now at the end. The way to generate the next word is we just take the last token in our text and convert. So we have a linear layer where the last token is input and the output is probability, or it's logits. It's like scores, which will get converted into probability distribution across entire vocabulary. So imagine every word in the vocabulary, 30,000, 50,000 words, gets a certain probability to be the next token. And then we can pick. So let me again explain this part. So we get a sequence of tokens. We will normalize them. We will just take the last token and convert last token to input to this neural network is token size, output is 50,000, vector 50,000 or whatever is the vocabulary size. And those will be just logits, just scores. And now we need to convert those scores to probabilities using softmax. So they all add up to 1 or 100%. And then we get probabilities over every token to be the next token, and that's how we can sample from that probability distribution or using some methods, etc. So that's the architecture of a large language model that we will also create. Now this can be also modified, all of these. So DeepSeek has its multi-head latent attention and DeepSeek sparse attention, which has a bit different architectures. I made videos about like how to code DeepSeek v3 from scratch. And this most important modification is the mixture of experts, which we will talk about. Instead of having one feed forward, we will have multiple feed forwards and a router that will pick where to send the token based on the token, which feed forward network is the most appropriate for this token, because some might be good for medical, with medical knowledge, some for math, some for languages. So based on the token, on the context, we're gonna send through different feed forwards that specialize in different things, and that allows us for every token to use just a lot smaller amount of parameters and computation. Instead of using entire feed forward for every token, we are just using like small part of parameters that specialize for that token. And so we don't need so much compute when we generate text. This is probably mainly for inference, for generating text later. Let's go through the code of the decoder-only transformer. Actually, I have a good tutorial. My video here, Code, Write and Publish AI Research Paper, Muon versus Muon Optimizer. I'm coding this LLM from scratch. So you can check it if you want. I'll leave the link below, but I'm gonna go quickly through code now. I would just like to show you this feed forward network because we went through the self-attention stuff, key query values, we went through that already. So feed forward is very simple. We have one linear layer from token size to the feed forward size, which is usually 4 times bigger than the model size, but it doesn't have to be. And then going from the feed forward back to the token size. And there is ReLU in between. So this is how it goes. We put X, which is our process tokens, after the attention mechanism through first linear, and then activate, and then through second linear. So that's how we pass that through this network, and it will be processed. It will, maybe new information will be added, etc. So it will go from this, expand 4 times, and then contract, and that's our process token now. And in transformer decoder block, we would define attention, feed forward, a norm, which is layer norm in this case, but you would use RMS norm instead. Maybe layer norm is simpler. And then dropout. And so first pass through the attention, then we can drop out some attention so it doesn't overfeed, doesn't depend on any neurons in particular. So make some neurons 0 randomly, and then add residual connection. So you are adding the input before it was processed with attention to the tokens that are processed. It's like keeping the old information as well. This is the residual network that I was talking, residual connection that I was talking about. And then normalize again. Now you see here we are normalizing after attention, but actually maybe we should normalize before attention. Just keep that in mind. Here we also, so this is the original implementation with layer norm and normalizing after the attention and after feed forward, but nowadays you would normalize before, which I will show you later in our code. Let me go to the last lesson here of the transformer. That's the expert. So expert, instead of having one feed forward, we will have multiple feed forward. So expert is just a feed forward again. And it's same, but now we will have multiple of these. So going back to the previous lesson, MOE router, let's say we have 8 experts, so 8 feed forward networks, and each token we will send to two best tokens for that, 2 best experts for that token. So this router is a neural network that will look at the token, and it will convert from token to probability, to logits, to scores, how much this token corresponds to every expert. And the higher the score, the more it corresponds. And we will pick 2 highest scores. And we will also have some way to make sure that a router is routing equal amount of tokens to every expert. So it's not just picking one or two experts, always two experts. For example, if we have 8 experts in total, and we pick 2 experts for every token, we don't want it to pick always the same 2. Which can happen because once it starts picking, it may realize that these 2 are learning most, so they know the best, so it's always passing into these 2 because they always know, they know most, because, and then it's like self-fulfilling, it's like positive loop where others cannot even learn anything because they don't get any tokens. And these 2 just keep getting all the tokens, so that's a collapse. So that's why we want to force the router to choose equal amount of, to send equal amount of tokens to every expert. So we call this class top K router. It's a linear, as I just explained, it goes from D model to number of experts. And top K is how much we choose, how many. Like 2, and number of experts would be 8, for example. And so we pass input through the gate to get logits. And then we have torch.topk to calculate the, to take the 2 highest of these logits. But I do recommend you just watch this video. I explain this in great detail and coded step by step for like everything about a mixture of experts. Now that we went through the course, let's go through the code. So we see all of these folders. I actually coded all of this from scratch in that course that I just mentioned. In this video, code, write and publish AI research paper, full course LLM from scratch, Muon versus Adam Optimizer. So it must be this exact one. There is another one that's similar title about publishing paper, but that's just 30 minutes. This one is 3.5 hours. This is the correct one for coding this from scratch. So watch this one. Okay. First, we have models. So we have components. I have expert, top K router, which I coded from scratch in that course that I just mentioned. A mixture of experts. So all of these classes. We have layers that contain rope, multi-head attention. What else? MOE transformer block. And then this is the class that just trains all of them. This is the large language model itself. Optimizers, Muon, and we use Adam from PyTorch. Experiments, 3 important. We first want to sweep learning rates. Test different learning rates to find the best learning rates for both of the optimizers. Then we can test different optimizer hyperparameters. If you just go like this is, I think this is simple to understand. So we test different like momentum and weight decay, and we find best ones. And then we also test like number of experts and the top K and load balancing weight. We just test different ones and find the best ones. I think 16 experts, top K, and this was the best one. So I just put this to our main script. And I think that's it. So you want to do this like hyperparameter search, hyperparameter sweep. You can see here the results. The lowest loss. We find the lowest loss and then use those hyperparameters. So this is the one, I believe. And just use these hyperparameters then. Number of experts, so it's 16. Usually you want to have configs separated. So this is the config for like 1 GPU small large language model, and this is for 8 times H100s, and that's it, I believe. Again, check this video. I coded all of it step by step in this video. And when writing the paper, technical report, whatever, you can use Overleaf or whatever latex editor, and you would just go slowly, understand everything, and write and describe what you did. Here is just a technical report on the large language model. You may first do it in Markdown and then convert later to latex, or you could just as you go, as you do research, or just keep updating and adding here. Now let's train this model. Let's start training on free Google Colab GPU. So I will copy the URL here of the GitHub repository, go to Google Colab and say !" git clone this URL, but oh wait, I need to click here, wait, connect, change runtime type and choose GPU, save, and then run. And then we will do %sign and cd to cd into this folder. So you see after my name, after slash, we have this folder. So we will cd into that. Actually, I will leave the link to this Colab below, so you can just run this without writing it manually. We need to install requirements. And then I will just copy the name of this file, trainmoe.py, and go !Python and run it. Let's see if it's training. It looks like it's properly training. It's downloading the dataset, converting it to tokens. And after it downloaded and tokenized the data, it seems like it started to train properly. So there is no bugs. And if we look at RAM, okay, so we can definitely increase the size of the model because it's just using 2.6 gigabytes. And actually it's not using anything. Oh, no, never mind. It's using most of the gigabytes of the GPU. So the model is big enough. And you see now we go to step 20. Now this is a bit slower because this GPU is a bit slower. So if you want to train this model to talk to you, you will need to wait a few hours and then make sure to save your model to Hugging Face or somewhere externally because it will interrupt because you have limited time GPU. So you need to save your model, train here, save, and then either wait for the GPU hours to reset or use different account. I'm not sure if Google is forbidding to use different accounts or not. You need to check this yourself, but you need to train the model in multiple sessions. So step 70, so it's just training and now it's just going. By the way, guys, this will clone my repository and run it, but if you are making your own LLM, either clone my repository or fork it, and then do your adjustments or create a new from scratch. And while you are editing your code here, you need to push it to GitHub, and then in Google you need to git pull. Every time you push changes, you run this pull, so you pull the changes as well. But I'm not gonna put it here for now. And that's how you edit in your code editor and then run on Google Colab. Also, there is extension for Google Colab. I'm not sure if it can be well integrated or not. I think it can. You can try that, it's a new extension. So that's my workflow. You can also check my video, my AI research setup, code locally run on Google Colab GPU or Cloud SSH. So you can check this video. So I'm gonna go ahead and interrupt because I don't need this one. So I'm just gonna disconnect and delete runtime so I don't waste GPU resources, and also for the Google and for myself because they will limit me later if I use GPU resources. I need to wait for it to reset until tomorrow or something. Now let's set it up on Hyperbolic. So actually I'm using Hyperbolic for the first time here. Let me train it. Let's see how easy it is to set up. I'm actually just wondering, I don't know how easy it is. So I'll go to my instances and rent a GPU now. Okay, it's down below. So it looks like all of them are taking 1, 2, and 4. So I can rent 8. I'm gonna choose this one. It's gonna be $11 per hour, 8 of them, which is okay. Let me just click next. Label, okay, Blueberry LLM. Okay, upload public key. I forgot how to do this, so let me check the support thing. So I have public key on my Mac, but how do I see it? I already generated it, so I'm gonna see it with this command. You may generate it if you don't have it. So also just ask ChatGPT, how do I generate public key on Windows or Mac? It's very easy. So I ran the command in terminal, it showed me my public key. You can also generate it very easily, and then I just copied it and pasted it. It's very simple. Okay, order summary, I'm gonna start building, let's see. It started in like maybe 10-20 seconds. It's spinning up the instance. It's now active. It actually took a bit longer to spin up. And it says here I can SSH with this. I just went to my terminal, pasted that command, ran it, and it works. I just pressed yes to generate the fingerprint, and it works. It's very easy. I mean, I typed yes, just read, it's gonna tell you. It looks like you can connect your entire IDE by adding this code. So whatever the name of the server, so you add your IP, and user is Ubuntu and host name, and then this is your file for your key. So here, SSH access, this is your username, this is your IP, and it's very simple. And now I can open this in code editor, not just through terminal. I explained this in the course, in the video I posted my AI research setup, a link below. So now I opened this terminal, I connected to the GPUs on Hyperbolic, and I'm gonna clone this repository, and I will just select this as the location, whatever, and now just wait a little bit. So this is very good. Now open. Now I can open literally my code ID within that GPU, like Hyperbolic GPUs. And this is very good because now I can just pip install requirements. Okay, we have some issues. Oh wait, we don't have any of this stuff. Maybe I didn't select template. Okay, ChatGPT told me to just, because I just copy pasted like my issues I had and told me to do this. Then I'm gonna do this. And it seems like I successfully installed pip with this curl. Then I need to add it to path. And now I can install requirements. I think it was very simple to fix it. So I just copy pasted it into ChatGPT, any issues I have. And now it's downloading. It all installed in maybe 4 minutes. I think it also installed PyTorch and everything. It looks like I need to run Python 3 command. So Python 3 train MOE 8x H100 Py. So that's my file that I have. It's actually generated by AI based on this train MOE. But let's see if it works, if it has any bugs. I think it should be pretty similar, so AI can generate it. Okay, it seems to be working. Number of GPUs available, 8. I also have this file, so if I run Python 3 utils/GPU monitor, so it took me about 13 to 14 minutes to figure this out. This is my first time doing this, so I had experience with other GPU providers setting up SSH to other GPUs, so it was, I think it's quick for the first time. Now I just need to figure out if they have like templates for like PyTorch and stuff, or I need to install it manually like this. But in either case, it's okay. It installs very fast in just 3-4 minutes. Now these issues are probably because of my code, not because of their GPUs. So let's fix this. So it seems like the bug was this version command, and now it should work. Yeah, now it works. Let's go. Okay, I can run GPU monitor. So now I have all of the 8 GPUs. I'm tracking how much of them are being used. So it does seem like the training has started. We are using every single GPU. Now we are grossly underutilizing these huge GPUs, but it seems like we are using all of them. Let's see. Oh wait, Sonnet made my LLM huge, 14 billion parameters and more. Oh my god, that's huge. But now we are using a lot more memory, 74 gigabytes of memory per every GPU. Now I don't see any computation going on. Yeah, we have some bugs, we'll fix it, don't worry. I actually just wanna make it about 300 million parameters, so I think 14 billion ran out of memory in one of the GPUs. Yeah, CUDA out of memory. So I think just 300 million is gonna train quickly. And if we have a lot of space available in GPUs, we will just increase batch size. Anyways, it finally finished. So these are the generations that I got. I showed them at the beginning of the video as well. That's the same model. So thank you for watching. You may join my school to become AI researcher. You can also check other courses on my channel, and see you in the next video. I'm gonna be publishing more of these AI research, writing research papers videos soon, very frequently.